If you're saying something, I can't hear it.
Am I on? Yeah. Okay. So let's get started. So welcome everyone to the first automata session of this year's POPL'. We're a bit late on time, so we will start right away. The first talk is remote. It's called Boundary Tree with Multiple Context-Free Grammars and Downwards Closures.
Yeah. Hi, everyone. Thanks for coming, and sorry that I couldn't be there in person. Yeah, as I said, I'm going to talk about bounded tree with systems, about multiple context-free grammars, and how to compute downward closures for these systems. I'm Lea Schütze. This is joint work with Aishwarya, with Pascal Baumann, with Prakash Saivasan, and Georg Zetsche. And I just kind of want to set the scene by taking an example. So imagine you're given some kind of complicated system, for example, an operating system. And on that operating system, you have programs that are running. And nowadays, these programs are probably multi-threaded, so they have several threads, each with their own processes, with their own stacks. And over the course of the execution of that program, you will probably switch back and forth between these threads with their stacks. And then occasionally the operating system will say, okay, different program now, and swap in, give priority to a different program. Again, separate set of threads, separate set of stacks. And this program will switch back and forth. Maybe we go back to the previous program. Maybe the user starts a new program. And now you have this really complicated system of interacting processes. And you would like to answer the big question, can the system reach some kind of undesirable state? For example, some kind of error state. And so if you just look at this, you might see immediately that this is undecidable in its full generality. Because even if you just had a single program with two stacks, it could already simulate a Turing machine, and then it's undecidable. So there's a couple of things we can do. So first of all, we bound the number of times that any given program by itself can switch between its stacks. And that is already sufficient to make the individual processes decidable. And then we will also compute the downward closure of the language of the whole system, which is basically possible because irrelevant spawns of programs that are never executed can be ignored. And that makes the analysis task as a whole feasible. So what are these downward closures? Okay, so imagine you're given some word, and now you can define an ordering between words. We call this a subword ordering, and basically the idea is that one word is smaller than another word if there is some kind of scattered embedding from the letters of one word to the letters of the other word. So pats embeds into parrots, so does art, so does pot. And then you get this whole set of words that are smaller than parrots, and that is a downward closure of parrots. And of course, we can then extend that to a whole language. Why do we like downward closures? Well, there's a long-standing result that tells us no matter what your original language is, the downward closure is always regular. And of course, if you have a regular language, then a lot of tasks become either feasible in the first place or much more efficient. Okay, so if we go back to our original example, we decided to make this task feasible by bounding the number of context switches, but that's not the only thing we can do. We could also instead bound the height of each stack, or the number of times that each stack can kind of reverse the direction, so switch between pushes and pops. And all of these bounds might seem a bit arbitrary, but in practice we have seen that even for small bounds, we can already detect a lot of relevant bugs in practice. But there's a bit of a problem to this because there's always these different bounds you can take. For each of these bounds, essentially, you have to find a new algorithm to compute the downward closure. And this is kind of where our contribution comes in. So we're starting with these systems that are all bounds on multi-stack automata. And there's a long-standing result or a sequence of results from literature that tell us that these are all equivalent to some model called bounded tree width, which I will explain in just a bit. And then our contribution is that we show that this is equivalent to another model called multiple context-free grammars. We do this other translation because it's a bit easier for our purposes to analyze. And then we show that if you have these multiple context-free grammars, you can find a succinct construction for the downward closure. Okay, so there's two systems here that I'd like to introduce in a bit more detail: bounded tree-wave systems, multiple context-free grammars. For the bounded tree-wave systems, imagine we're given a really simple system that has access to two stacks. So the system can push and pop A's from one stack, and it can push and pop B's from the other stack. And now we're looking in more detail at one specific execution of that system. So we might start by pushing an A on one stack and push a B on the other stack. And you can see at the bottom, I'm starting to draw this linear graph, which is basically just a sequence of the steps of this execution. Might push another A, might push a B. Okay, and now we have popped a B that we have previously pushed. And in our execution graph at the bottom, we add an arc to kind of pair these two states. State 1, where the B was pushed, and the state 3, where the B was popped. And then we continue. We push a B again. We pop an A. So we draw an arc again. We pop another A. We draw another arc. We pop the last B and draw the last arc. And let's say that is our execution. And now we have this run graph at the bottom, this execution graph. And of course, as for any graph, you can find a tree decomposition for that graph. And that kind of already gives you a flavor of what we're looking at. We're saying a language has K bounded tree width if there is some formula in MSO logic that defines a set of run graphs, and the set of run graphs that the subset of those run graphs that have tree width K is exactly the language we're looking for. Okay, so that's a bounded tree width language. And then the other model we were talking about were multiple context-free grammars. So a normal context-free grammar, we probably all know, you have this set of non-terminals, you have some terminals, and the non-terminals can derive sequences of terminals or non-terminals. And then multiple context-free grammars kind of generalize this by asking, okay, what if we add multiple registers to each of these non-terminals? So each of these registers can now contain its own word, and these are kind of derived jointly. So you can see the S terminal, the S non-terminal, that still only has one register. A and B both have two registers. And these rules now not only tell us which non-terminal go to which non-terminal, but also how to rearrange the registers. So you can see the S rule, for example, tells us, okay, if I have an A with registers X1 and X2, I can concatenate the contents of these registers with some separator symbol. Or alternatively, the B non-terminal I can always construct with a single B in each register just from nothing. You can see that I draw these arrows the other way around. That's just, I think, notationally, because I think it's a bit easier to think about multiple context-free grammars as being built up from the bottom up instead of derived from the top down, but really it's equivalent. Okay, here's the derivation tree of a multiple context-free grammar. You can see it looks exactly like a normal derivation tree, except we're writing down all the contents of all the registers at each step. And these are strictly more powerful than normal context-free grammars. For example, we can derive these copy words, which are just a word and then the word repeated, which a normal context-free grammar cannot. A second. Okay, I want to give just a brief overview of how we show that these two systems are equivalent. Don't get too hung up on this because I'm going to skim over it fairly quickly because I want to talk more about the downward closure. But just to give you a hint. So we start with a bounded tree with language. So this consists of bounded tree with run graphs. And then we can show that we can find a tree automaton for these run graphs that accepts these run graphs. And then from a tree automaton, it's fairly simple to construct a multiple context-free grammar. And in the other direction, we start from the derivation trees. We add some edges that basically tell us where one component, where one register starts and where it ends. And then we can show that these graphs that we that result from that are in fact MSO definable. Just a brief overview. If you want to have more detail, either find me afterwards or read our paper. The other thing that I want to talk about, obviously, is how to find succinct construction for the downward closure. And I think for that, it's helpful to consider how we construct downward closures for normal context free grammars. This is a long-standing result from Courcelle. It's called Courcelle's construction. The idea is that if you have a really simple grammar like this, for example, and you have any tree that is sufficiently long, then you will have a path in that tree that repeats some non-terminal several times. And if you have that repetition of a non-terminal, that means you can either cut it out entirely or you can repeat it multiple times. And for the purposes of the downward closure, that means that you really just need to look at the alphabet that is produced alongside that loop of non-terminals, because obviously the order now doesn't, for the downward closure, the order really doesn't matter because you can repeat this as many times as you need and then drop all of the letters that are not in the order that you want. So we just look at the alphabet and we repeat this alphabet as many times as we'd like. And so we introduce these rules that are called accelerated productions because in some sense they allow us to do multiple derivation steps in one single transition. So in some sense, we'd like to apply this construction directly to multiple context free grammars. But these several registers that these multiple context free grammars have, they give us some challenges. So first of all, in a multiple context free grammar, it's possible that only individual components, individual registers are acceleratable. As an example, if we have a derivation tree like this, you can see that, in the first component of the Ds or the S's, you can kind of accelerate these A's because you can produce arbitrarily many A's. But if you look at the second register, you can't really accelerate the second register. It will only ever contain a single letter. And even if you can identify kind of which components, which registers are acceleratable, you can in fact shuffle these around. So you also need to be aware that potentially something that is acceleratable in one component might be acceleratable in another component later on. And lastly, even if you have done all this work to identify which components are acceleratable, you can't just ignore the other components because there might be dependencies. So here's an example. I have two derivation trees for the D non-terminal. And you can see on the left, this is acceleratable because I can have as many A's as I'd like. And on the D, this is not acceleratable. It ends after one step. So I know that I can accelerate in the first component. I can put as many A's as I want to. But there's a dependency here that tells us, okay, if I accelerate in the first component, then my second component must contain a B because the transition that puts a C in the second component will not lead to a derivation tree that is acceleratable. Okay, so how do we approach this? First, we want to identify which components are acceleratable. And here is some derivation tree. And now I'm gonna kind of draw these connections between the non-terminals in a bit more detail by looking exactly at which components go to which components. This we call an embedding map between the non-terminals. And so we can see, okay, from the S to the C, X and Y both go into the first component, Z goes to the second component. We can continue this up to the A non-terminal and then continue this up to the S non-terminal. And the point is that we are looking for these embedding maps between non-terminals that are idempotent. Why are we looking for idempotent embeddings? It's because remember that Courcelle's construction relied on the fact that you can essentially repeat a loop as many times as you would like. And if we have an idempotent embedding, then this means that this function, this embedding, will always be the same, no matter how many times we repeat this loop. And so the fixed points of this embedding is exactly where we will accelerate, because everything will flow into the sides from this into these registers. Okay, so we know where we want to accelerate. We don't really know what to put into these accelerated components. For this, I'm going back to this derivation tree and imagine, okay, now we're looking at just the fixed points of these embeddings. So the X and the Z, because that ends up in the first and the third component respectively in the top. And now let's look at the D on the right, for example. We can see that the D, the first D of that D non-terminal, that kind of joins the X in the C non-terminal, and it joins from the right. Imagine this kind of as a river. The fixed point of the embedding from X to X, that is kind of the main river, and then there's little letters flowing in from the side. So we can see that D ends up in the first component, and in particular, it gets concatenated to X from the right. So this is our alphabet sigma 1 right, of all the letters that can occur on the right. Similarly, the other D can join Z from the left, so it's in sigma 3 left. And that kind of tells us what our alphabets are. Okay, so now we just need to figure out how to deal with these dependent components. And I'm going to show you next a very complicated derivation tree, but don't worry, we'll simplify it in just a second. So again, we start by identifying the fixed point of our embedding from the S to the S. Everything else from the S component at the bottom flows into the first component. And now we want to accelerate this register at the top. So we introduce these alphabets, sigma 1 left, sigma 1 right. We take them to the cleanest star because we're accelerating. And then we are introducing a new non-terminal for now on the left. That is just basically the S from the bottom, but we just restrict it to the first component. And we do that because essentially what we'd like to do in the end is cut out everything in between. So this kind of helps us shorten our derivation tree in the end. And then we are, okay, we have now this accelerated register at the top. And we can see that the B non-terminal, its first register is now irrelevant, right? Because it's already subsumed by these watershed alphabets. So we can essentially ignore the first register. And so we introduce a stack-rated version of the non-terminal that tells us, oh, we only care about the second register now. And the same thing happens here with the A non-terminal. But here we need to be a bit more careful, right? Because here we see, okay, there is actually a dependency here because that D, that is the third component of the A, that only can, that might be a dependency, right? Because it tells us this D can occur because it is occurring on that path from S to S with the embedding we're looking for. And so we can't just project the other two away. We still need to make sure that we are only taking the appropriate derivations. So what we're doing is we are annotating this non-terminal with the target non-terminal and with the embedding that we'd like to guarantee. And we continue this process going down to B. We can now see, I mean, B is essentially empty at this point because all of its components end up in the watershed. And but it's just here to kind of verify that we find the correct S in non-terminal. And we go down to S, which embeds into itself with the identity mapping. Okay, and then we are done. And you can see that this non-terminal, this derivation tree is now much simpler than the one we started with, and it's shorter, which is the important bit. So I've shown you kind of how to take a multiple context programmer and how to shorten it. And if you have a sufficiently short automata, if you have a sufficiently short tree, you can just write down an automaton for it. But I kind of promised you some kind of succinctness. So how small do these trees really get? Okay, so imagine you're given some kind of derivation tree. And now we pick out any path in that derivation tree. And if that path is sufficiently long, then we know we have some kind of non-terminal type that gets repeated over and over. And we can write down the embedding maps between these non-terminals. And now there's a result from Ramsey that tells us if that graph of the same non-terminal type and its embedding maps, if that graph is long enough, if it is big enough, then there must exist one clique that is monocolored. And monocolored here means obviously, because the colors are our embedding maps, this means that the embedding from the bottom to the middle and from the middle to the top and from the bottom to the top are the same. Well, that means that this must be an idempotent embedding, right? Well, but then this is the point where we can do our shortening procedure that I described earlier and cut out everything between the top and the bottom non-terminal, and that shortens our tree. And Ramsey's theorem tells us that this essentially is a constant. It's not a constant in the number of registers of the grammar, but because we're always talking about bounded trio systems, we can assume that the number of registers is constant, and so the whole tree height just becomes polynomial in the number of steps. Thanks, I'm almost done. Okay, so just to recap, we have shown that bounded trio systems are multiple context free grammars. We have used these embedding maps to identify the points in the derivation trees where we can accelerate productions. We can use decorations to ensure that the non-accelerated components have all of the dependencies satisfied. And we can bound the maximum height of these derivation trees via Ramsey's theorem. Yeah, and this is the end of my presentation. Thanks for listening. If you have any questions, I'm happy to take them now.
So does the tree width appear as some parameter of the multiple context free grammar? For
example,
it's
not a one-to-one correspondence, but it roughly corresponds to the number of registers in the grammar.
So be here, for example, the maximum arity of any non-terminal?
Exactly, yes, that's correct.
See. And when you do the translation from MCFGs to the tree width, is that the maximum tree width that you get?
Yes, again, it's not one-to-one, but they're in semi-linear correspondence to each other.
Okay. And do you have some optimality around that?
No, I don't think we looked at the optimality of that.
Okay, thank you.
No, I don't think so.
Let's thank the speaker again and move on to the next talk.
Okay, thanks everyone.
So the next talk will be given by Aurel Barrière. It is one of the distinguished papers this year with title Formal Verification for JavaScript Regular Expressions, a Proven Mechanized Semantics and Its Applications. Yeah.
Thank you. And this is joint work with Victor Deng and Clément Pitt-Claudel. And I know that judging by the title of the talk, it looks like I'm about to tell you about regular expressions, but I'm not. Because this is a talk about JavaScript regular expressions. And these modern regular expressions, or regexes for short, are just different from your traditional regular expressions. And they're different for several reasons. First of all, they are not regular anymore because we added some new features that increase expressivity. And it's actually quite easy to build a regex that will match the language of duplicated words, a language that is famously non-regular. But also, the matching problem itself is different. With a traditional regular expression, the matching problem is simple. We're trying to decide whether or not a given string belongs to the language recognized by the regular expression. It's a simple yes-no question. With a regex, however, things are different. Given a regex and a string, we're trying to find a substring that is matched by the regex. And if there are multiple ways to do so, we should return the substring which has the highest priority. Now, different regex languages have different ways of expressing which is the match with the highest priority. But most of them today mostly agree on what we call backtracking semantics, meaning that we should return the match that would be found first by a backtracking algorithm. This means, for instance, that the first match in the string has priority, explaining why if I'm trying to match D or B on that string ABCD, it will return B and not D. But also, this junction is no longer commutative because we're going to try the first branch first, meaning that R1 has priority in that example. And so if I'm trying to match A or AB on the string ABC, I'm not going to return the longest match, I'm going to return just A. And finally, whenever we have quantifiers like the star or the plus, the priority should be to try and iterate them as many times as possible. Meaning that in that example, of course, B star is going to match all of the Bs. Now, because of these new features and this new matching problem, modern regex semantics have become increasingly and surprisingly complex and subtle. We have plenty of features and edge cases. To make things worse, each modern regex language is different, meaning that, for instance, JavaScript regex semantics are not the same as Python regex semantics. If we take a look specifically at JavaScript, in JavaScript there is an official document, an official standard telling you how to execute any JavaScript program, and this is called ECMAScript. And this standard contains a full dedicated chapter to JavaScript regexes. So we have a huge dedicated regex chapter, and it's more than 33 pages of specification describing with pseudocode and English how to execute a JavaScript regex with a backtracking algorithm. So if we want to reason about those modern regex semantics and those modern regexes, we would need semantics that are both faithful to a real-world regex language, with all of its subtleties, and that are also practical for formal verification. And this is precisely what we do in this work. We provide faithful and practical semantics for JavaScript regexes that we mechanize in Rock. And to show how practical they are, we provide multiple applications. We formally verify some regex equivalents, and we verify a matching algorithm. Now, those two qualities, faithfulness and practicality for formal verification, can sometimes be at odds with each other when designing formal semantics. And we can even see that in related work about JavaScript regex semantics. In fact, there has been multiple kind of attempts. One of them is actually our previous work in collaboration with Noé de Santo. And this was called Warbler. And in that project, what we did is that we did a line-by-line translation of these big regex chapters that I was showing you before. And so we have thousands and thousands of rock lines where for each pseudocode line of the standard, we wrote an equivalent rock line. Now, clearly, this was faithful to the standard because for each line, we have an equivalent line. But also quickly, this becomes not really practical for formal verification. Even though we managed to prove a few properties with Warbler, some of them are quite complex to prove. Because we have like thousands of lines of a big rock fixed point and so on. But of course, when we think about semantics for regular expressions, we think about the nice inductive style semantics that we have all seen before. And we could simply try to extend that with JavaScript regex features and this new matching problem. And in fact, this has been done before multiple times in other papers. Now, of course, the question is it faithful? Sometimes it's difficult because it's very different from that official JavaScript standard. And in fact, a few years ago, there was a semantics that had to be fixed 1 year later because some feature was incorrect, and there could be other problems. And also, while this is clearly more practical than Warbler, we show in this work that we can even do better and have some properties that are even more practical for formal verifications. So let's just quickly recap about some of the features that we have to deal with in our semantics. Of course, we have all of the traditional features from regular expressions, but we also have so many different ways to match characters, like character classes and so on. We also have plenty of ways to do iterations. We have the star and the plus and others. This one, for instance, is going to repeat a regex from n to m times. And then we have an interesting feature that we call a capture group. So in modern regexes, every time you have a sub-expression inside parentheses, the engine should not only return the substring that was matched by the whole regex, but we should also return the substrings that were last matched by each sub-expression inside those parentheses. And so in that particular example, I have a capture group because I have B star inside parentheses. And so the engine should tell me that the whole regex matched AB, and that this capture group last matched the string B. And so that is the expected result. We also have another very interesting feature, which is called look-behinds. I won't go too much into details, but it allows you to match the string backwards. So you had some position in the string, and then you have to read the previous character and then the previous character again. So that we have to take into account when designing the semantics. And of course, we also have look-aheads, anchors, back references, and so many different flags that can alter the behavior of matching. Okay, so how are we going to give semantics to all of these different things? One of the insights in our paper is that the best way to reason about those backtracking semantics is not with a backtracking algorithm. Instead, we're going to define another kind of big step style inductive semantics that we like, but with something a bit special. We're not going to relate a regex and a string to some result, like the result of matching. We're actually going to relate a regex and a string to something that contains a bit more information that we call a backtracking tree. And this backtracking tree, you can think about them as a sort of execution trace of a backtracking algorithm on that regex and that string. So here is an example. This is a backtracking tree of the regex A or C inside the capture group or AB on the string AB. And whenever you want to try to match this regex, you have to do a choice between matching the capture group on the left or matching AB on the right. And so this is why our backtracking tree begins with a choice node at the top. And then the branches of the tree are ordered by priority. So we put on the left what has the most priority, in that case trying to open the capture group and match what's inside the capture group. And on the right, of course, we simply try to match AB, and then we find a match. Whenever we go inside the capture group, so on that side, we again have a choice between trying to read A or C. If we tried to read C, we would fail because there is no C in the string, and so that's why we get a mismatch. But of course, if we try to read A, we could simply finish, close the capture group, and return a final match. Now, before I tell you how we build these backtracking trees, I want to tell you why we like this kind of semantics. And one of the big advantages, of course, is faithfulness, because we have a huge rock proof that states that the leftmost match leaf of this tree is always equal to this warbler mechanization, this huge line-by-line mechanization that we did. And so if you trust warbler, then you can also trust our semantics. Also, one very important feature for practicality is the fact that this actually contains more behaviors than a backtracking algorithm. Because a backtracking algorithm typically starts after finding the first match. It would never even consider the other possibilities. And in that example, it would never even see the second branch and the third branch. But in the later slides, I will show you how having those extra behaviors is actually great to reason about sub-regex equivalence and to reason about some matching algorithms that will explore those extra paths that a backtracking algorithm won't see. Finally, a third advantage, and I know this slide might look a bit scary, but actually with only 21 nice inductive rules, we can completely isolate the control flow of all JavaScript regexes. And so this is complete for ECMAScript 2023, and we only use those inductive rules. I want now to take a closer look at the semantics, and we will begin by taking a closer look at the semantic states. In our semantic state, we have a couple of things. We first have this L, which is a list of things that we need to match sequentially. So initially, this is just the regex you want to match, but then this will increase as you do the matching. And the things are mostly regexes, but we will see that we can add some other things too. Next, of course, we have an input and a position within that input, the string, of course. We have a value of the capture groups that we will need, and we have a matching direction because, as I told you before, there is one feature that allows you to go backwards. So this can be either forward or backward. And next, we can look at one of our semantic rules, and I suggest looking at the rule for the star. So let's say that in my list of things to match, the first thing in that semantic state, I have R star followed by some other list. We want to also to match something after the star, but let's focus on the star. Now, clearly, every time we have a star, we should have a choice, because we can choose between iterating that regex one time, or maybe more, or we could choose also to match nothing with that star and just skip it entirely and go on with whatever is left. So, of course, in our tree that we evaluate to, we have a choice node and we have two subtrees. And the tree on the right, the one with the less priority, is quite easy. It should be the tree that corresponds to matching L, whatever was after the star. Now, the tree on the left is a bit more complex because, of course, we decided to iterate the star, and so we should match the regex R a first time, and then we should match the star again because we can do more than a single iteration, and then, of course, we should match L, whichever was next after the star. If we stop right there, there will be an issue if you're trying to match a regex like epsilon star, it will not terminate. But the good news is that the JavaScript semantics tell you how to avoid those cases. It tells you that you should check after each iteration of a star if you have made some progress in your inputs compared to when you first entered the star. And so in our list of things to do, we also add this kind of check things that will cut short the branch of the tree if you have not made any progress, and otherwise we'll keep matching and keep matching. And so this is just one of our rules. Of course, this is very simplified because actually we need to reset some capture groups. We need to take into account the greediness or laziness and maximum or minimum number of iterations. But this is the main idea that we saw for the star. And now that we have these nice semantics, we can actually use them to reason about some things. And one of the applications that we verified is equivalence. And we'll see that we need to define what it means to be equivalent. Regex equivalence has multiple real-world use cases. For instance, it is used in some regex engines, but it is also used by some regex optimizer to try and simplify regexes. So formally, when is it the case that two regexes are equivalent? Now, a naive definition, the most intuitive one, is to say that two regexes are equivalent when given any string, they return the same result. And that seems to be exactly what we want out of equivalent regexes. However, this definition is not entirely satisfying to us because this definition is not a contextual equivalence, meaning that you can have sub-regexes that are equivalent, but if you put them into a bigger context, then finally the bigger regexes are not equivalent anymore. And we can see that on an example. Using that definition, epsilon or A is clearly equivalent to epsilon or B, because for any string, they will simply match the empty string because epsilon is on the left of the disjunction, so this has priority. But of course, if we put them in a bigger context, like C epsilon or AC and C epsilon or BC, you will find different results. Because, for instance, the first one will find a match on the string CAC, but the second one won't. So if we want to try and fix this to get a contextual notion of equivalence, what we can do is take a look at the backtracking trees of those two bigger regexes on that string CAC. And if we zoom a little bit on the subtrees that correspond to executing the sub-regexes epsilon or A or epsilon or B, what we might see on that first tree is that the only match leaf that we can see used the second priority way of matching the sub-regex, not the first one. And so if we want to get this contextual equivalence, we will need to reason not only about the top priority way to match a regex, but also about all of the many different ways to match that regex. The good news is, of course, our semantics is designed to showcase all of these behaviors, and so we can simply do that, and we can do a new, stronger notion of equivalence, and we say that two regexes are equivalent when for any string, if we take the backtracking trees of those two regexes and that string, we will have the same list of match leaves at the end of the trees. Again, this is very simplified. You can actually remove some leaves, but this is the main idea. And we can then prove that this is actually contextual. And so if you have two sub-regexes that are equivalent using that notion, then even in a bigger context, they will be equivalent. and this allows you to reason locally about subregexes. Using these definitions, we could actually verify some equivalence from the real world. And so, for instance, we looked at a JavaScript regex manipulation library that is called regextree. And this library contains an optimizer. And so in this optimizer, they do the following optimization, where if they see the same regex quantified twice, they will just merge the two quantifiers by adding up the minimum and maximum number of iterations. And this looked completely correct initially, but of course it's not. We found some issues, and we also looked at some conditions under which the optimization can be performed. Interestingly, this depends not only on min1 and max1 and so on, this also depends on the matching direction, meaning that sometimes you can perform the optimization only when inside a look behind, and sometimes you can perform it only when outside of a look behind. Another application that we verified is actually a matching algorithm, and we decided to verify what we call the PyVM algorithm. You can think about this algorithm as an extension of NFA simulation, but extended to support backtracking semantics and capture groups and other features. So what this means is that we are going to compile the regex down to an NFA, an extended NFA with some priority edges. And then the algorithm is going to find the top priority path in that NFA that corresponds to the string. This is linear time algorithm. It supports most regex features, and this is used widely in Rust and Go, and even for JavaScript, because V8, the engine of Google Chrome, for instance, contains an optional engine that uses the PyVM. But despite being widely used, this is also quite tricky to get right, especially for JavaScript. 2 years ago, actually, we showed that the usual way to do the PyVM is incorrect for JavaScript semantics because it has a unique way to check for progress in stars, the things that we were talking about before. The good news is that we designed a new NFA construction and changed the algorithm a bit. And with this new construction, at least it should work for JavaScript semantics. And now we wanted to prove it. Of course, we have a lot of challenges in that proof. We, of course, have to prove compilation correctness because we're going to compile that regex down to this NFA. This NFA is actually going to be represented with a bytecode, so we need to verify all of this. Also, this PyVM has quite a peculiar execution order. It's going to do a mix of breadth first search and depth first search, so we need to prove that this is going to return the top priority match. Also, in order to be a linear time algorithm, this algorithm is going to prune some path of the NFA when it corresponds to a configuration like an NFA state and a string position that it has already seen. So we need to prove that we're not going to miss any match this way. And finally, because we modified it for JavaScript semantics by changing the way we check for progress, we also need to prove that this is correct. Let's focus for a short while on this exploration order. And one of the key insights is to say that if backtracking algorithm corresponds to a depth-first search inside a backtracking tree, then surely this PyVM exploration order must correspond to some exploration strategy on a tree. And this is precisely that algorithm, this exploration strategy of a tree that we use in our proof. We write down an intermediate algorithm that works only on a tree and that does this kind of exploration strategy. So it mixes a depth-first search and a breadth-first search, and it is also allowed to prune subtrees, just like the PyVM algorithm was pruning some paths of the NFA. Let's look at an example. Let's say that we have this backtracking tree of the regex A star or A followed by B on the string AB. And so our algorithm is just going to take this tree as input, and it's going to do a depth-first search until it finds a read. And then it's going to explore other branches until it finds reads. And when we have found all of them, we're going to move on in the string and then do another depth-first search until we find another read. And then we do the same for the other side. But then on the other side, we realize that we are seeing a subtree that we have seen before. And so this subtree is going to be pruned entirely, and we're not going to search among it anymore. Finally, we can return and finish the algorithm by finding this match leaf. Now, it's very convenient that this has the same exploration order as the PyVM algorithm because the first step of our proof is then proved by simulations that those two algorithms always return the same result. And then finally, what we can do is prove that this exploration strategy always returns the first match leaf of a backtracking tree. And conveniently, this proof has nothing to do with bytecodes or NFAs. It's just a proof about trees. Finally, of course, because we have connected our semantics to Warbler, we can also connect this result, meaning that we have a full correctness theorem that relates the semantics of this PyVM algorithm to the actual ECMAScript standard that describes what JavaScript should do. Now, those semantics and these proofs are only the first step of a bigger project, because now we would like to develop what we call Linden, a formally verified linear time engine for JavaScript regexes. Now, of course, we have multiple things to still do. We have to provide verification of an implementation and not just a verification of an algorithm. And then we have many optimizations and other algorithms that we should try and verify. We could also extend this PyVM algorithm, because 2 years ago, we showed that specifically for JavaScript semantics, it is possible to match in linear time unrestricted lookarounds. So we could also add that to our existing proof. And of course, we would like to do more equivalence proofs to have a full verified JavaScript regex optimizers. These backtracking tree semantics can also be used in other ways. We could use them for other languages, because each language is different. And we are also verifying right now the complexity of different subsets of JavaScript regexes. Now, some of these projects are already done. Some of them are ongoing. And for the rest, we would love to hire new students, either in Switzerland or in France. So feel free to reach out. Thank you.
Couple of questions. Any questions in the audience?
Hey, thanks for the nice talk. Your new equivalence semantics, do you know whether this is equivalent to the previous observational semantics inside of a context?
So we can prove that this implies observational equivalence under any context. But then there is a very interesting question of, is this the weaker possible equivalence that would verify that property? It's not something for which we have a proof, and our current intuition is that it could be the case, but that it won't be the case for a new feature that has been added now since 2023, which is duplicate capture groups. And I think we would need to first adapt this to support duplicate capture groups, and then maybe we would have the weakest possible equivalence relation that satisfies this property.
Thank you.
Any other questions? Yeah.
So thank you for the nice talk. I would like to follow on Damien's keynote in the morning. So how much is this reusable for the other flavors of regular expressions like Python, .NET, and stuff like that?
This is an excellent question, because this is one of the projects that we are working on right now. It really depends, but mostly we believe that this can be used for many other semantics. Clearly, .NET, for instance, we were looking at it because it checks for progress differently, but it seems like we could also support it. We could also support some flavors of longest match semantics just by looking which of the branches goes the farther. There are some of them that are quite surprising. For instance, the Java semantics uses backtracking semantics everywhere, but not inside look-behinds. And so for this, we still need a bit of work to figure out how we could adapt it. But so far, everything seems to point to the direction that it should be possible.
Thank you.
Thank you.
All right, let's thank Aurel again. Okay, so the next talk is going to be given by Han Su, with title Network Change Validation with Relational Netcat. Go ahead.
Okay, so let's get started. Today I'm going to talk about network change validation with relational netcat. I'm Han. This is a joint work with Dave, Ratu, and Zach. To begin with, I would like to say networks are large, therefore it is very hard to maintain them. Network companies like Microsoft, Google's, or Rogers all suffers from network misconfiguration, which has brought them millions of loss to themselves and to the society. Therefore, it is important to develop some kind of automated tool for us to debug the network. And that kind of tool is called network verification. Most network verification in the context can fall into this kind of category. Given a static snapshot of network N, such as the network here, I show 4 devices like device A, B, C, D, and thousands of other devices which is not shown in the picture. I also show some of the link between these devices. So given a network like this, we want to make sure it is safe. We want to ensure properties such as reachability, whether a packet sending from device A can finally reach device D, or we care about loop freedom, such as packets sending from device A will never reach A again. During past 2 years or so, network change verification has achieved great success. However, this notion of network verification doesn't fit into the development of network. And let's see through an example. Suppose you are a network engineer and you are taking in charge of the network here. One day, you find all the link towards device D becomes unstable, so you like to take device D down for inspection and for maintenance. During the time for maintenance, you would like to make sure that the network still functions correctly. So you decided to make an update. That is, you decided to reroute all of the traffic through device D now through device B. And everything you want to make sure is that you have to make the update correctly. However, this kind of change is really hard to capture in the traditional network verification. In traditional network verification, we will give a set of property P for the pre-network. This network contains thousands of devices, so that the property P is a very coarse and approximation towards the network. Such as, if we care about the reachability property, it will contain millions of reachability pairs. Instead of stating this reachability pair one by one, we only state the reachability between some of the devices we are interested in. And then we go to the new network. We'll state another set of property P prime, which may or may not be the same with the property P. But this property P prime is again too coarse to capture the change you have made, such as the reachability between some very far away device will never be able to capture the internal rerouting you have made. And you definitely don't want to state the change by looking through this network with thousands of devices and millions of reachability pairs. So the question is to ask, can we focus on the change itself instead of doing so on the whole new network? So this notion of network verification is called relational network verification. In relational network verification, the problem is stated as follows. Given us pre-network N old and a new network N new, is new network updated exactly from the old network under the change specification S. And our job as a programming language researcher is to develop a language to describe network changes. Of course, we are not the first one to do so. There's one prior work called RELA, which focuses on one particular network change called path change. Originally, you are forwarding data through the device A, B, C, and now you are going it through A, D, C. In our work, we would like to demonstrate relational netcat, which focuses on generalized notion of change, which is trace change. The trace is a sequence of packet, PK0, PK1, PK2, representing how packet is modified and transmitted inside the network. So what are traces changes, and what is relational netcat? Let's move on to our next section, the language design of relational netcat. The first concept I would like to introduce you to is the idea of traces. Here is an example network with 7 devices, A, B, C, D, X, Y, Z. And I here show 2 of the example traces, the right trace above and the blue trace below. The right trace above shows how we forward a packet from device A, finally reaches device Z, and it contains 4 packets. Each packet contains important header information like source IP, des IP, protocol type, as well as the location information, such as the packet 1 here denoted has a location field B, denoted that it is now transmitted to the device B. In certain point of view, or in the language of netcat, we view the network as a set of all possible traces, such as this network will be represented as a set of red trace and blue trace. This idea of viewing network as a set of traces suggesting we are treating the network as a system of how to transmit and modify packets from devices to devices. Now we have the idea of traces. Next, we can come to our problem. We are going to make the rerouting from the device B and device C. How are we going to do this? How are we going to describe this? So next, we are going to formalize it and formalize the network changes. So let's restate the problem. Originally, we got a network written in the netcat denoted by KO'd, which contained two traces, which is the red trace and the blue trace. Now we are going to make the rerouting from AVDZ to the ACDZ. So here we change the red trace to the green trace. Now we got a new network, which is a new set of traces contains the green trace and the blue trace. So the problem now is how are we going to describe network changes? A simple idea is to describe network changes as trace relation, which is the set of trace pair. In this case, we'll describe this change relation as a red to green trace pair and blue to blue trace pair, suggesting that a red trace in the pre-network corresponds to a green trace in the post-network, while the blue trace remain unchanged from the pre-network to the post-network. Using the triangle as a notation of applying a trace relation onto a trace set, our verification goal can be stated as K-old under the trace relation R change is equivalent to K new. So now we have the idea of network and network changes. The next step is to introduce the design of relational netcat, which is what are the anatomics for describing this R change relation. So this network change contains two trace pair, which is red to green, blue to blue. Let's first focus on the red to green trace, which is a trace pair of PK0, PK1, PK2, PK3 to the rerouting of itself. So first thing first, let's first view at the things happened at device A, which is before we enter in device B, nothing has changed at all. Therefore, the first anatomic we need to describe this kind of trace relation is a relation suggesting nothing has changed at all. And we would like to use the construct of ID or traces, suggesting that all of the traces should be mapped to itself. Nothing has changed from the pre-network to the post-network. How to describe it? We will use the language netcat. In netcat, a netcat expression is interpreted as a set of traces, and the set of all traces can be expressed using the language netcat. Therefore, the first construct for our language relational netcat is IDK, suggesting that all of the traces belongs to the netcat expression K should be mapped to itself. And then let's move on. Since we have dealt with the things happen at device A, the next step is to do the things at device B and device C, where we have a rerouting from where we reassign the location field B to location field C of the packet 1. Therefore, we introduce two new constructs, which is delete seg, insert seg. Delete seg location assign B, followed by insertion seg location assign C, suggesting we are doing a reassignment of the location field from B to C. Combined with the things we talked on previous slides, we can now describe the things happens at device A, B, C, which is ID or traces, delete seg, and insert seg. Putting things together, now we can describe, now we can have three new language constructs, which is delete seg, insert seg, and the regular concatenation R1 with R2. Finally, let's finish the discussion about the red to green trace relation. Now we have dealt with the things happens at device B and device C. And next, we move to device D. Since nothing has changed at all after the rerouting, the packet 2, packet 3 should remain unchanged in the post network. Therefore, we again assigned an ID or traces at the end of our language specification. So here, the R reroute suggests all of the traces that has gone through a rerouting. Similarly, we can describe the things that has not be changed from the old network to the new network, which is the I preserve. We use the language ID or traces, location doesn't equals B. All traces, location doesn't equals B is a netcat expression suggesting all of the traces doesn't go through device B. Using ID, we are suggesting that all of the things doesn't go through device B should remain unchanged from the old network to the new network. Combining all these things together, we can finally state our specification for verifying the rerouting happens in this network. That is, the K-old triangle R reroute plus R preserved is equivalent to K new, suggesting all of the things in the new network is the things that have been rerouted and preserved from the old network. So this is the design of our language relational netcat. We reorganized and decomposed the language construct we talked on previous slides into 4 basic but essential atomic, which are filter, map, insert, and delete. Besides, we also add the regular union, regular concatenation, and the regular star to compose this atomic into larger language specification. So here are all the things about the language. So the next step is how are we going to check this specification? What is the algorithm for this kind of compilation? As one familiar with automata theory might notice that relational netcat is actually the netcat transducer. So the question is to ask whether we can apply the regular transducer algorithm onto our relational netcat. And the answer is, in most of the steps, it is true, but with one exception. Here is the whole compilation pipeline for checking K-old under the relation R change is equivalent to K new. Everything flows smoothly when we apply the regular transducer algorithm, but with one exception, which is the projection. It will induce a blow-up of at least the packet space size. It is really large because a 32-bit packet will lead to a 2 to the 32 blow-up here. So what's happening here? Let's first see the projection step on the regular transducer and the regular automaton. So here is how our automaton accepts a word. It will start with a state S0, and each time it takes an input alphabet, and then it goes to the next state, S1, S2, and finally to the Sn. And in our projection step, we first get an input of a regular transducer, which is length preserving. And this length preserving regular transducer will accept a pair of letters on each step, which is A1, B1, then it goes to state S1, S2, and finally to the state Sn. What does the projection step here do? It converts the regular transducer into the regular automaton by projecting the input alphabet of transducer onto its second opponent. That is, we are going to eliminate all of the letter A inside the transducer so that every rung of the regular transducer will correspond to a rung inside the regular automaton. But things are slightly different in netcat automaton. And here is a rung of a netcat automaton, and you can see the difference here. Here, each state is paired with a packet, which we call a configuration. So what does this kind of configuration do? It actually faithfully represents how a packet is handled in the network. In the network, each device takes a packet as an input, then modify it and forward it as the output. So inside the netcat automaton, each time it takes the last input package, which is the packet 1 prime, and then modify it and forward it as the packet 2 prime. Promote this idea of configuration to the netcat transducer, we got a configuration of a packet pair, representing a packet relation from a packet in the pre-network to a packet to the post-network. Then the things goes wrong. That is, when we're going to do the projection, we not only need to project over the transition alphabet, but also over the configuration. There is no simple way to do so, and the regular transducer algorithm will make the PK1 explicit, which will directly induce a blow-up of at least 2 to the 32. So how to solve this problem? Let's get back to our first principle. Why are we going to design this language? Because changes are small. What does it mean by changes are small? And let's see through the netcat transducer. Here is a rung of netcat transducer, start with S0, PK0, PK0 prime, to Sn, PKN, PKN prime. And it actually faithfully represents a trace translation from PK0, PK1, PKN to the PK0 prime, PK1 prime to PKN prime. The changes are small here suggests that the trace translation from the trace in the pre-network shouldn't be too different from the trace in the post-network, which suggests that the packet at the corresponding position should be not too different from each other. That is, PKI should be very similar with the PKI prime. And this gave idea of the key technique of our projection algorithm. That is, we should split the configuration by how much we change the network instead of the whole packet space. We'll classify the configuration by the PKI prime pair instead of the whole packet space. We were very happy to tell you the actual technical meaning of this sentence after you finish reading the paper, but for now, let's move on to our next section. Okay, since we have made an empirical or kind of philosophical observation as our key techniques, so the question is to ask, does it apply to the reality? So we performed an evaluation. We implement our language in the OCaml, and we combine our technique with all of the data structure optimization techniques that use the previous work. We use BDD, anti-mirror derivative, and by simulation-based equivalence checking. And we also implement an interface for Batfish and Rela so that we can take the raw data input of these two tools and then verify it and give you the output. The first benchmark I would like to show you is a benchmark comparing with Batfish, which is a benchmark which currently no relational network verification tool can re-implement. So Batfish is a network verification tool in terms of the traditional network verification. Inside of its tutorial, it provides you with an industrial benchmark with over 200,000 lines of routing table information written in JSON. And during that tutorial, it guides you through step of changing the network, then verifying it. And in our work, we try to reproduce that procedure in our language as much as possible and give 5 test cases and their time. As you can see, all of the test case falls down below 30 seconds, which is perfectly suitable for our goal of iterating network by updates. The other benchmark I want to show you is the benchmark comparing with Rela. So Rela is a relational network verification tool where they use the Alibaba internal network, which contains more than 2,000 of devices and 20,000 of traffic classes. And we compare our two on their data set. We randomly select 2,000 traffic classes out of 20,000 of traffic classes on 3 of the most commonly used Rela specification and reinterpreted in our language. And these 3 specifications are preserved. That means you didn't change the network at all. The node deletion suggests you remove a device from the network, and the forwarding path change suggests you reroute a device to another. And the average of our work and the Rela all falls down within 1 second. So it is suitable for us to iterate the network by updates using this kind of verification tool. And the other thing I want to mention you is that our algorithm or our observation actually applies. That is, our algorithms falls down 1 second, but using the traditional naive transducer algorithm, it will directly time out over all benchmark on all the test cases. So to conclude, the key takeaway I want to give you is networks are big, but changes are small. Therefore, when doing network development, we should describe and verify the network changes instead of doing so on the whole new network. And if better, use our language relational netcat, for it is designed for this. And thank you for your attention.
Yes.
Thank you for the very interesting talk. So I was wondering, you showed the performance, and you showed that you said that the philosophy is you described the changes aligned, basically, right? PKI, PK prime I. But what if you have a change in the network that maybe extends your trace by 1, right? So then you would have okay. How would it perform, and could you adapt your technique?
Yeah. Thank you for your question. This actually is some point we omit in our talk. That is, we directly goes to the projection step here. But before the projection, there is a step called cross product and epsilon elimination, which will turn the transducer, which may maps the words of different lengths into a transducer that is length preserving. Yeah, so there's a pre-processing before this projection step, so that we only need to care about the length preserving mapping in the case. So we can also treat we can also deal with the non-length preserving trace translation using kind of delete and insert. These two are non-length preserving.
I don't know. Maybe that's what you're saying, and but on the next slide.
Sure.
Or the slide where you say our philosophy. Yeah, exactly, this one, right? And if you go to the next transition, here, right, So when you have two different, just so that answer, when you have two different traces from two different networks, where in one network, after the change, you actually have to do one or two more hops. Like, how is this compatible to this splitting of the configuration?
Sorry? Can you repeat the question?
If you have two traces and one has, but maybe we can take it offline.
Okay, sure, no problem.
Any other questions? Actually, we do have some time to elaborate on this.
Yeah, hello. So just to understand something, I mean, you are reasoning all the time about traces. So, but modifying a graph could imply that you have to reason about an exponential number of, I mean, I can modify one node, and this will generate, the modification of an exponential number of traces. I'm just wondering, whether it's a practical way, let's say, or a powerful way to reason only about traces when you talk about changes in graphs. So, you see what I mean, or? So, for instance, admit you have like a central node.
Yes.
And all the paths go through that one. See, and
yes.
Now you want to modify that one, change it with that, and some number of nodes and so on, and direct some whatever edges around and all these things.
Yes.
See, I mean, here there is a lot, this will touch a lot of traces. All the traces of your system will be touched by this little modification.
Yeah.
So I'm just wondering whether
okay.
you could have this situation. So because you see, I mean, in your slide that we see here, you say changes are small.
Yes.
Maybe local, what you mean.
Yes.
At a trace.
Yes.
But the number of traces that you have to deal with and how to describe these changes is complicated in general, right?
Yes.
So is this an issue of your approach or no?
Thank you for your question. I think there are two aspects for this question. The first is the traces are not as large as 2 to the 32 as we, in our work or in the previous work, we treat them symbolically. It is actually very small compared to the 2 to the 32, though it is still very large compared to the constant number. And the second question is, can our work deal with large change? The answer is yes, but kind of the starting point of our work is to treat kind of this kind of small change. If you can make small changes and you can make large changes. You can just destruct all of the infrastructure in the old network and build a new one from scratch, and you can call that also a change. We can also describe this, but in this case, you should use traditional network verification tool because you can make little use of the knowledge you had on the pre-network towards the post network. And but in terms of the networks are usually very large so that nobody knows actually what is going on globally. So every time the network engineer makes an update, they only make a small update so that they want to make sure the things doesn't go out of their control. And our tool is designed for them so that they can verify each time they update the network.
Maybe to ask the previous question in another way, have you analyzed the complexity of these kinds of verification problems, and can you characterize kind of when relational netcat would be a win versus maybe some other approach without
we only performed our evaluation in terms of the seconds, but we didn't perform a serial analysis because kind of the key techniques we rely on is kind of empirical or hard to quantify over. But in terms of the complexity of each step for algorithm, we believe it is aligned with kind of previous work catch paper, and I think it is currently the fastest version of checking this kind of netcat equivalence.
Yeah, one idea that might be interesting, there's an old paper by Tim Griffin in the database community, and he looks at incremental view maintenance. So totally different problem, but the same kind of incremental optimization, and looks at how, as the size of the change grows, the benefits of incremental view maintenance start to diminish, and there's a tipping point where it's just better to recompute. And I wonder if there's a similar characterization you could give for this kind of calculus.
Yeah, we believe it's true, but sorry, we didn't have that in our paper.
Okay, let's thank Hannigan and move on to the last talk.
Okay, mic check.
So the last talk of this session is given by André Lengal on parameterized verification of quantum circuits.
Okay, thank you for the introduction, and welcome everybody to the first quantum talk of POPL'. We are still in the automata session, so if you came for automata, don't run away because there will be a lot of automata here. This is a joint work with several people. Some of them are in this room also. Ufunction, Qnao, and Ram are around, so if you're interested, just catch any of us, and we will be happy to talk about this work. So just a brief outline. So if you're not familiar with quantum, I will start with a very short introduction into quantum circuits. Then I will try to give you some general feeling of how the verification of quantum circuits look like. And then I will go for introducing our new formal automata and transducer models that we use for describing and reasoning about parameterized quantum circuits. So let's start with 101 on quantum circuits. So I guess you all have seen some classical circuits. So in a classical circuit, we have some wires, we have some gates. And if you want to talk about the state of a classical circuit, for example, at the end of this small circuit, then you can say, so the state is some assignment of 0 and 1s to the wire. So if you look at all the possible assignments of 0 and 1s to the wires, then the state in the classical circuit will be one line here will have the value 1. We are exactly in one state. In quantum circuits, this is a little bit more complicated. So quantum circuits, they look somehow similar to the classical circuits with some specialties, like all of the gates have the same number of inputs and outputs. Also, you cannot copy a state because of the no-cloning theorem and stuff like that. And here, the state of a quantum circuit is a little bit different. We are not in one state at the same time, but we can be in some superposition of states with some probabilities. So you can see here I'm in 4 possible states with an equal probability. But actually, I was lying a little bit. We don't have probabilities, but we have complex numbers. So we have complex numbers which are called amplitudes. Their probability that they represent is taken by taking the modulus of the complex number and squaring it. And of course, it needs to hold that all of the probabilities sum up to 1. So this is how a quantum state looks like. Let's look at what a quantum gate is. So for classical circuits, classical gate is just a truth table. You have seen this many times, I guess. For quantum circuits, a gate is a unitary. A unitary is a matrix such that its inverse is taken by its conjugate transpose. So not going into the textbook on linear algebra, this is just the thing that the gates are unitaries are telling you that everything is reversible, which is the property of quantum mechanics. You have no cloning, and you have norm preservation, which means you are not losing probabilities on the way. You still need to keep the sum of probabilities to be 1. OK, so you are now experts in quantum. And let's talk about parameterized quantum circuits. So what I showed before is just some normal quantum circuit, and I want to talk about parameterized quantum circuits because many of the circuits given in the literature are parameterized by the number of qubits that you use. If you're coming from the quantum background, then usually people, when they talk about parameterization in quantum, they are talking about some rotation angles. The size of the circuits are the same, but the rotation angles inside the circuits are different. So what we are talking about is size parameterization. So we want to verify quantum circuits where the size is a parameter. And examples of these circuits, I said before, there are many of them. For example, generalized GHZ circuit, Bernstein-Vazirani, which is given in this example here. So you can see that the number of qubits here can be is arbitrary. We have these ellipses here, so we can put there more qubits. Grover's search is parameterized, error correction codes, arithmetic circuits, quantum counting, quantum phase estimation, which is the basis of Shor's algorithm, quantum Fourier transform, which is also used in Shor's algorithm. So all of these things are parameterized circuits. So let's go to the verification of quantum circuits. So how our framework works is that we are working with these whole triples that you have seen many times because you're at POPL'. And in this case, the whole triple, we have a C, which is for a circuit. And we have a set of states for a precondition and a set of states for a postcondition. In this case, the C is a parameterized quantum circuit. And the meaning is that if we execute C from some state which is in the set of in the precondition, then the obtained quantum state terminates in some state which is in the postcondition. So very similar to something to the classical Hoare logic. A general approach how to do verification is that you can take some representation of the set of the precondition, of the set of quantum states in a precondition. You use some kind of abstract transformer, if I use the names from abstract interpretation, to compute the set of states after I run a circuit. You can do it by, for example, taking the whole unitary of the circuit and doing some matrix multiplication and stuff like that, or you can execute gate by gate. And in the end, you test this inclusion of what you obtain with respect to what is in the postcondition. Now the big thing is how to do this representation, because I'm talking about parameterized quantum circuits, and there are unboundedly many of them for some particular case, and we will need to be talking about infinite states of quantum states. So the quantum state that you want to represent, so I have a commonly occurring set of states, which is a uniform superposition. So this is a state which is used often in quantum computation. You usually start an algorithm by putting all of the qubits in a uniform superposition, and then you do some magic. So you need to be able to express the uniform superposition. This is essential for many quantum circuits. So you want to be able to express this. So these are vectors of complex numbers of the size, for example, 2, 4, 8, and so on. And if you look at the probabilities of these guys, so you need to take the modulus of this number and square it, then they sum up to 1. So this is for a set of quantum states. For the circuit, so we're talking about parameterized circuits, so you need to be able to express in some way an infinite family of circuits that look similar. So there is some example of some parameterized circuit that uses some common pattern. Like it starts by taking this kind of downward staircase using the U gate, then it's doing controlled not here, and then it's using this upward staircase using some gate W. And we want to have this representation such that we can test the inclusion of what we obtain after running the circuit with the states from the precondition and what we have in the postcondition. Now, let's go a little bit more to the automata side, which is regular model checking. So regular model checking is a popular approach for verification of parameterized classical systems. And there are many flavors of regular model checking. But in general, regular model checking is an approach for solving this question that I talked about before, when pre and post are represented by some kind of automata, and the circuit, or in general program, is represented by some kind of a transducer. Then the set of states obtained by running some system from some precondition is then obtained by taking the image computation of the transducer with respect to the precondition, and the inclusion is done by checking language inclusion on the automata. Now the question is, like, which automata and transducer models are suitable for reasoning about quantum states and circuits? So let's start by looking a little bit a different view of quantum states, which is that I want to persuade you that quantum states are actually trees. Why are there trees? This is the amplitude table I showed before. So what we can do is like push it a little bit on the top, it will fall down, and then we can build this nice tree on top of that. So you can, this is a tree, as it may look very similar to something like binary decision diagrams we have seen before. And it holds that for a quantum system with n qubits, you will have a tree which will have 2 to n leaves, and the tree will be perfect. So perfect tree means that all of the branches are the same length. So now if a quantum state is a tree, and I want to talk about sets of quantum states, so what is a good way for talking about set of trees? We are in the automata session, so it is some tree automata. So, but there are many flavors of tree automata, and let us look again at this uniform superposition set of states, which is useful in quantum computation, and which tree automata model should I take to express this thing. So I want to express trees that look like this, a set of trees that looks like this. And if I look at the standard tree automata, then they have a problem that they are very regular. So regular means local, so it means that I cannot really synchronize these sizes of the tree. So I cannot, using tree automata, I cannot have perfect trees, because if I'm looking at a run of a tree automaton through the tree, I go to the left, I go to the right, and these two branches are completely independent. So I have no way to express perfect trees in using standard tree automata. So last year at POPL, we introduced a new automata model called level synchronized tree automata, which has some synchronization over, which has some global synchronization over the levels, which is able to express perfect trees, but it cannot express unboundedly many amplitudes. So what we need here, if we want to express the set of all possible superpositions, we need unboundedly many amplitudes. The problem with the level synchronized tree automata is that we still have a finite number of leaf symbols, so we cannot express these things. So let's talk about our new formal model called synchronized weighted tree automata. So how does it look like? So for simplicity, I will not talk about internal labels of trees. We have them, but for the presentation, I will avoid them. So the automaton is a 5-tuple. We have a set of states, which is standard. It is finite set of states, similar as the finite automata. We have this omega, which is a set of colors or choices, which are used for synchronization. We have a transition function, which I will describe later. We have one root state, and we have a set of leaf states. And the automaton accepts the tree by starting at the root of the tree from the root state. It goes down, and in order to finish branches, it needs to come to some leaf state. I will describe this semantics in more detail later. So in this synchronized weighted tree automata, we have the standard tree automata, but we put there two more things. The first thing is the synchronization, which is something that we already had in the previous model, but let me describe it in short. So if you look at the standard tree automata without any synchronization, so we have a root state Q, which can make these two transition. It can go down to QQ, or it can go down to UU, and U is a leaf state. Then it can accept these trees, and you can see that some of these trees are nice, but some of them are not nice because they are not perfect. For example, this tree here is not perfect because one subtree is smaller than the other one, also this one, also this one. So these trees are not perfect, so this is a problem with using standard tree automata. If we have a synchronization, so the synchronization works by labeling transitions by some of the colors. And then there is a property that if you look at the run of the automaton on a tree, that at every level of the tree, the colors of the transitions taken by the automaton needs to be the same. So if you're at some level, so let me show you a picture. So if you're at some level, you need to, all of the colors at some level need to match. So this needs to be the same thing. And this allows you, for example, to express the set of perfect trees. So this is one of the very interesting and important set of quantum states. You can use this to express the computational basis states. So these are all the classical states where there is no superposition. So this is just the classical states. And the LSTAs can be used to express this, but they cannot be used to express the uniform superposition states because, as I said before, we need an unbounded number of amplitudes. And that's a problem here. So we need to introduce something more. And the something more is weightedness, that now the states are given, or the transitions are given weights. And the transitions now look a little bit more like this. So you can see that now, in addition to the previous thing, I have some weights here in the transitions. And these weights are telling us, if I look at the tree automaton as a generator of something, that I go down the tree, I start in the root state, I go down the tree, and if I go down the level with some weight, then I keep multiplying the weights on the branches. So you can see that I label the tree with some weights on branches, and then if I finish in a leaf, I just multiply everything which is on the branch. So this concrete automaton can be used to express this set of uniform superposition states. And in general, we need to have a little bit more general form of the transition. So we don't only have weight, but we have some kind of linear forms here and also here on the left side and also on the right side, which are telling us that we need to combine some different runs of the automaton. So the semantics, if you look at it as a generator of this transition, is that I will, if I'm in U and I want to take this transition, I start by inductively taking a tree which would be generated by P, taking a tree which would be generated by Q, multiplying each of them with the corresponding coefficient. By multiplying, I mean I go to the leaves and I multiply all of the leaves there with the given value. I will sum them together, for which they need to have the same structure. So I'm only talking about the perfect trees which have the same height. And then this will give me the tree for the left side. I will do the same thing for the right side. And there I will construct the final tree by just taking the left tree, right tree, and taking one node as their root. The language of this automaton is then given, as usual, is just a set of trees that are generated by A. So what are the properties of these automata? So language union, the model is closed for language union. The proof is very simple. You just merge the transitions together. You may need to relabel some choices, but that's easy. Language complement, they are not closed, and how to show that they are not closed under the language complement, that's very simple, because if you just look at the number of possible trees that have complex values in the leaves, then there are uncountably many of them, so you definitely cannot express that. What is nice is that language emptiness is p-space complete, so it's decidable, it's p-space complete. The membership is done by just quite simple subset construction, which is just keeping the track of the frontier of the states, and the hardness is done by a reduction from finite automata universality. But these are pretty much like all the nice things, because we have intersection non-emptiness, which is undecidable, because we can encode PCP into it. So this is the first undecidable problem. From this, it follows that language intersection is that we don't have closure under a language intersection. Why? Because we know that emptiness is decidable, but we have undecidable intersection on emptiness. And language and equivalence, language inclusion and equivalence is also undecidable, for which we have a proof from reduction from emptiness of a Turing machine. So this inclusion and equivalence undecidability is a kind of bad thing, because we need to do this when we are checking, when we run our algorithm, we're checking that the states that we obtained are a subset of the postcondition. So this is bad. So this seems like, okay, so this is a nice model, but it's actually not useful because we cannot use it for verifying quantum circuits. But actually, we have an alternative, and the alternative is do not talk about the language of the automaton. Let's look at something else, and what we have is we talk about the tree function of an automaton. Because as I said before, we have these kind of synchronization colors, and we can see an automaton to be a mapping from sequences of these colors into trees. So you can see as a tree function of the automaton, we take sequence of colors into trees, and example how this look like is, for example, for some automaton, it can represent that a mapping from 112 into this tree of the uniform superposition. So you can see the automaton as a function from trees, from sequences of colors to trees, and this is very useful because because what we can do is that for every computational basis state, which we often need to talk about in a quantum verification, we can have a one-to-one mapping into a tree, into a color and into the sequence of colors, and that gives us a mapping into a tree. And also that when we compute the image, we preserve this mapping of sequences of colors to trees along this computation. So this gives us a power to do relational verification. What we can do is that we can verify that if we started from one quantum state, we came to a different quantum state. We don't have this like a mix-up of, we don't know, if we look at the postcondition, we don't know what the resulting quantum states originated from. So we have this kind of relational property that we have in our verification. And this is very powerful because we can actually, seems that we can actually do more than we would be able to do if we just check for the language inclusion. And we can also use this for showing doing circuit equivalence checking. Because for doing circuit equivalence checking, we just need to, if we have two circuits, we just need to start both of them with the computational basis states. There are like 2 to n, many of them. And we can look at the automata we obtain as the results of the computation, and we can check functional equivalence of the automata. And if functional equivalence holds, then we know that the circuits are equivalent because they are encoding unitaries, and by linearity, we know that we only need to check if we have a unitary with dimension n, we can only check like n many independent vectors. So this tree function is a very useful thing, as I try to persuade you. And we also have a tree, so the questions we are worried about are tree function equivalence and inclusion. So we want to check that the tree functions of two SWTs are the same, or they are at least included. And the question is, well, how to do this now? So We took a different problem, but is the problem actually solvable? Because the original inclusion wasn't. So the good thing that it is solvable, it is p-space hard, and it is in X time. And the interesting thing is how to show so what is the algorithm? So how to decide this? So if I want to show the algorithm for the tree function equivalence of two automata, the first thing what I do is that I check the equivalence of their domains. And this is easy because the domains, as I said, they are mapping sequences of colors into trees, so the domains are some sequences of colors which can be expressed by some finite automata. So first thing is we take the domain DFAs of these two automata. We check whether they are the same. If they are not the same, we know that the functions are different, so we can terminate here. Otherwise, we compute the automaton which represents the minus of these two SWTAs. So the minus means I have an automaton that will represent the trees which are obtained by taking the two trees for the particular word of choices and doing minus of them. And then I can check that what I obtain, the automaton generates only 0 trees. And this can be done by transforming the obtained automaton into a linear transition system. So this is a finite system when I have a bounded number of complex variables, and I have linear updates of edges. And I'm wondering what's happening in this system. So we want to check that we only obtain, at some interesting states, we only obtain zeros, the result of zeros of doing this linear updates, which can be done by running the famous Cars algorithm. So if you don't know about Cars algorithm, this is an algorithm that takes the linear transition system and deduces all affine relations between the variables in the systems. This is a very nice algorithm. I recommend you to look at it if you don't know it. Very quickly, weighted tree transducer. So we have a regular model checking approach. We have automata, and we also need to have transducers. So we also introduce a corresponding tree transducer model. So it looks very similar to the automata. For the sake of time, I will only show the transitions, which look also similar, with the new thing that we have left here and R here, which means left and right subtree, because transducer needs to take a tree and convert it into a new tree. And these transducers are very nice because we can have a compact representation of parameterized gates by transducers. Before we were using some specialized procedures, which was not so nice. Composition is quadratic, image computation is quadratic, equivalence inclusion checking is X-time complete. So this is a very useful model. Okay, and we also have a way how to obtain these transducers for parameterized circuits automatically for some patterns. So for example, for the Hadamard transform, we have this very simple transducers, which is doing this uniform superposition. And for some more general patterns, we have a way how to obtain a transducer that can do this kind of behavior of some fixed-sized gate. So let me go to evaluation. So we implemented this in some C++ prototype, and we tried to verify several circuits, Bernstein-Vazirani algorithm, carry ripple adder, some syndrome extraction, and quantum error correction. And also equivalence checking of two classes of circuits, Grover's algorithm and Hamiltonian simulation, where we are checking equivalence of optimized and non-optimized circuits. And you can see that in many times we managed to verify the circuits under 1 second. The hardest problem was this adder, which is strange because it's not a quantum circuit. In principle, it's just a reversible classical circuit, but it has some complicated structure of what's happening there. So the transducers there were getting quite a big, so it took the longest time. To conclude, so I introduced a new automata and transducer model, which is very interesting for capturing parameterized quantum circuits. It is expressive, but we still have decidable this tree function equivalence and inclusion property, which allows fully automated verification. And for future work, we have some ideas how to extend this model with recursion, because what we want to do is quantum Fourier transformation. That is a very important algorithm in quantum, and we want to have a parameterized version of it. And we want to also work a little bit on the engineering side to have some fully automatic conversion for open QASM files. And the next thing also is support for measurement. So before I finish, this is automata session. Quantum and automata are a very good match. I try to show that now. And if you're working in automata and you would like to also try the flavor of quantum, please try. It is very interesting. There are very interesting problems there. And let me end with that. Thank you.
Time for one quick question.
Yeah, thank you for the talk. So in general, we use projections as predicates for preconditions and postconditions, but I saw that here you're using sets of states. Mm-hmm. So how would this change if you considered projections instead of just sets of ensembles?
Yeah, so this is, you're talking about like quantum Hall logic, right?
Yeah, pretty much.
Yeah, so I think we are incomparable with quantum Hall logic, so it is a different approach. We're thinking about how to combine them together, and I think it's something for future work.
Okay, sounds good. And how would this verification look when you have like noisy circuits?
We don't consider that. We just look at the very fine ideal circuits.
Thank you.
There was another quick question, maybe?
Thank you for the amazing talk. I noticed that the test case for Bernstein-Vazirani had a fixed secret. Mm-hmm. Could this formalism deal with unknown secrets and a given oracle? Like, for example, for Deutsch-Josa, if you had an oracle for f of x, could this deal with any f of x with the promise of half and half?
Yeah, okay, so that's a very good question. So in this example I have for Bernstein-Vazirani, the secret is somehow fixed. It's parametric, but it's fixed. We have a ways how to do it for also any secret. So for that, we need to somehow generalize the oracle. It's possible, but we can do it manually. But in general, we come to the problem of it depends on how you really write down the precondition and postcondition. But we came to the problem of that we need to do language inclusion. And in the case where we have more than one choice, the language inclusion is already undecidable. So we could do it manually by doing some kind of minimization of the automaton and then just showing isomorphism. But we don't have like a complete procedure for this case. But I think that it should not be difficult to do it.
Great, thank you very much.
Okay, let's thank Andre again.
Okay, hello everyone. My name is Noam Zilberstein. I'm going to be the chair for this session on concurrency models. We have 4 really great talks for you. The first talk is going to be given by Enrique Roman Calvo on arbitration-free consistency is available and vice versa.
Thank you so much for having me. This is a joint work with Hagi Tatilla and Konstantin Enea. And in this work, we focus on storage systems because storage systems appear in our daily life. For example, imagine that you go to a conference like in Rennes, and you need to book a room. Then most of us do it using some application that internally has some storage that reads that the room is available and then writes that the room is no longer available, I just booked it. And this diagram with application and storage is very easy to understand, to imagine how the structure of the application looks like, but it doesn't really apply to real implementation. Like if you think about a real implementation of storage systems, they look more like this. Instead of having all the information stored in a single place, in a monolithic scenario, we have a distributed system where the information is distributed across different replicas connected through some network. So at the end of the day, all the information is available, but the access to the system doesn't become a bottleneck. The system is not often distributed, but also replicated, meaning that the same information may appear in 2 or more different nodes. That makes the system more resilient in case there is a crash of a failure of the system, right? Because if some node crashes, you can still retrieve information as a backup server. And those distributed replicated systems are great, right? Because you improve the performance, you make it more resilient until you actually have to use them. Because one of the main issues of distributed replicated systems is consistency. We expect them to guarantee some notion of consistency, and it's not always trivial, right? Let me show you with this example. We have 2 clients that want to book the same room. So for example, we have some client here that use the application, I book the room. The update applies to the replica it connects, and the updates on a replica doesn't immediately transmit to the whole system. So there is a moment in time when the system has 2 different versions of the same information, one that the room is available and the other that is taken. When the second client tries to book the room, we expect some notion called strong consistency, meaning that the client observes the latest version, so the room is taken, right? But what it can really happen is that the information that the room is taken arrives later to the client that the room is free due to some problem in the network. So at the end, the second client observes that the room is still free, so book it. And unless they are friends, they will have to share a room, which is not an ideal situation. Actually, talking about ideal things, we could think about what are the properties of an ideal storage system. We just mentioned a strong consistency, the property of strong synchronization between replicas. As other ideal properties, availability, meaning we want to reply to our clients immediately, don't have to wait for the network to coordinate. And the third property is partition tolerance. That means that in case of there is a crash on some replica, we'll still be able to reply to our clients. Unfortunately, the CAP theorem says that you cannot have the 3 properties at the same time. In fact, partition tolerance is a not negotiable property because in a distributed system, replicas may and will fail due to the nature of the system. So there is always a trade-off between availability and strong consistency. Sacrificing availability means making our system slower because we have to synchronize. So it's often the case that instead of providing strong consistency, we provide weaker notions of consistency. So what does it mean to provide weak consistency? Let me show you with an example. Here on the left, we have a program with 2 clients, one that writes X and Y, and the other that reads X and Y as well. Under strong consistency, we expect the clients to observe the latest version. So the executions are essentially like this, like the first client, let's say, write X and Y, and the second client observes both writes of the same of the client because they have to observe the latest version. On a weak consistency, clients don't necessarily observe the latest version. They can, but they may not. So for example, under some notion of weak consistency, an execution like this can actually happen, where the first client is executed, but the second client only observes the write on Y. The write on X may not be visible due to some problem in the network, right? And this is not an admissible behavior under strong consistency. A particular case that you may be familiar with of weak consistency is called causal consistency, where we expect information to be observed transitively. So for example, this case, where the second client observes y but not x, is not valid under causal consistency, because if you observe y, the write on y, you should also observe the write on x, because the write on x happens before the write on y. That's the notion of transitively. However, under causal consistency, you could still observe phenomena not admissible under strong consistency, as we saw here, where you observe the write on x but not the write on y. So causal consistency is a particular case of weak consistency, but one can imagine that there are many other models. And why do we care about weak consistency? Because the thing is, even if we have a strong consistency that you cannot implement it in an available manner, causal consistency you can actually do. So there is always a trade-off between the consistency that you provide and the properties that your storage system can have. So in this work, we focus on which class of consistency models can be implemented in an available manner in the case of a network partition, in the case of our system that has to be partition tolerant. And we focus in a very general scenario when we have multiple operations, right? Because when the application uses a storage system, the storage system may impose some requirement, like you have to use some particular API that can go from simple put and get operations that read a single object or write a single object, to more complex operations like SQL that can affect you an unbounded number of objects on your system. And I say that we have to focus on the operations because there are particular consistency models, like this one I present here, the conflict-preserving causal consistency, that on simple operations like put and get, you can implement it in an available manner, but on more expressive operations like SQL, you cannot do it. So this problem is actually hard to resolve. So just a quick recap in case I lost some of you here. What we have here is an application that communicates with a distributed system that we assume there is partition tolerance from here onwards with some operation. And in the middle of this, we have a consistency model that talks about the semantics of these operations. And then we can ask ourselves if the system can be available or not. Okay, good. We are actually not the first one investigating those results, as one can imagine. Like for example, here, there were two independent groups, Mayahan and others, and Atiyah and others, that found two independent, incomparable conditions for a multi-value store to be implemented, for not being implementable in an available manner. While beyond those negative results, as we mentioned, causal consistency can actually be implemented in an available manner for the particular case of the key value store, right? But the problem of those results, where they are nice, as the title of the slide says, they are partial results. They don't answer completely the question. There is not truly answer to the question. Well, until now. What we present here is the arbitration-free consistency theorem, a tight characterization, an if and only if condition that says when an implementation can be available, can admit an available implementation. And this condition that we found arbitration freeness, that we'll present in a second, has a nice corollary. They say that the strongest that one can implement is causal consistency, meaning the positive result I just presented, it coincides with the best that one can do. And that actually corresponds to the intuition that the distributed community had, that causal consistency, you can implement it, and anything else is probably not. Okay, so this is what we prove. Let me show you what this condition exactly means with, again, the recap. This is where we are. The application, the system, and then we ask if we can do it available or not. Okay. So, as we said, the corollary said that you have like a strongest model that one can implement. Hence, we first have to talk about all possible consistency models. And for talking about all consistency models, you first have to have a framework for defining consistency models. For us, a consistency model is a set of visibility formulas that indicate when some write instruction, like a put, is visible to some get instruction, some read. And we say that the put is visible to the get if there is a change of path dependencies a sequence of events that has to happen before, between the put and the get, so the put is actually visible. And this change of dependencies, it may involve, for example, a session order indicating that something happened before another instruction if they execute the same replica. Or, for example, read dependencies that once something happened before other if something is written, or even writes an object that is written by someone else. We can also model communication we received before to model that some instruction has to be received before executing a second one. And we can also model in our framework arbitration. Arbitration is a particular specific relation that deserves its own slide. And basically, it's a total order between events that acts as a tiebreaker in the case of concurrency. So to put an example, imagine that you have 2 put instructions and you have some get that should read from somewhere, right? The arbitration tells us where you should read from. So for example, if the second put happens happens after the first put, then the get will read value 2. Well, if it's the opposite, then it will read value 1. This arbitration is like a last writer wins a conflict resolution policy that it's a global order, as I mentioned, and is often using different models to exactly for this reason. But not always, right? Other conditions that I presented, like receive before, possession order, etc., they are not global properties, they are local properties, because you can essentially depend on my replica, my instruction, what I observe or what I don't. So it makes sense to distinguish between those models that depend on this global order and those models that only depend on local information. And that's the exact condition that we have. The arbitration freeness is a condition, say a model is arbitration free, it can be defined with as arbitration. For example, causal consistency is arbitration free because it can be defined only using communication, while sequential consistency, a weak version of a strong consistency, it's not arbitration free because it always requires this arbitration. This definition is nice, it's cute, but it's not only that, it corresponds to the exact condition that we found in our theorem. Because, and basically it makes sense, like the causal consistency or corresponds to the intuition that causal consistency you can define with arbitration and you can implement it with in an available manner, sorry, whereas sequential consistency you cannot do it and it's defined with arbitration. So now we know what we want to prove, now we know the condition that we found for the proof. Now let us go to what actually the proof works. Well, a very schema of that. At an if and only if condition, we can, the proof is divided in 2 parts. Okay? The first part, showing the arbitration free is available, the first part of the title of our paper, is actually pretty simple. Because if our model is arbitration free, one can prove that it's actually weaker than causal consistency. And causal consistency, we know that you can implement it in an available manner. Therefore, an implementation of causal consistency is an implementation of your arbitration-free model that you want to do. So that's the easy condition, that's pretty easy. The hard part is actually the vice versa condition, that showing that the model is, that the implementation is available, your model should be arbitration-free. And actually, we prove it the contrapositive. So if it's not arbitration-free, then it's not available. And that implication, we prove a contradiction. So it's a bit complicated, but basically what we have is implementation that is available, but that provides a non-arbitration free, and we show that this scenario is impossible. Try to find a contradiction. Okay? Hope I didn't lose you so far. And basically, this is like a bit of a sketch. Because your model is not arbitration free, we can construct a particular program that will lead to a contradiction. And basically, because your model is not arbitration free, there is a visibility relation that uses arbitration. Makes sense, that the model is not arbitration free. With that visibility formula, we construct a program a la CAP, meaning inspired by the original CAP theorem proof, that if in the case, for example, here they have a visibility with n+1 events, then your program is executed on 2 replicas, each of them with n+1 events. But there is some kind of symmetry here to make the construction work. So basically, the first part of the events before the arbitration is executed on one replica, and the other part of the events are executed on the second replica, and vice versa. We require that the first instruction should be a write instruction, the last instruction should be a read instruction. The instruction in the middle depends on or in the definition of your visibility, but you can always find something. And we require, and that's important actually, that if your last instruction is a get on X, no one in your replica will write on X. Only the opposite replica can write on X, but yours cannot. With that idea, with that particular construction, then we can show actually the contradiction. Because if our model is, your implementation is available on partition tolerance, we can observe that it's partition tolerant, we can assume that there is no communication, right? Because the network can be totally disconnected. And then, yet an unavailable implementation, all instructions have been executed. Hence, you have a trace with all instructions executed and no communication happened. In that scenario, the get on X here must read X from somewhere. It cannot read it from the first replica because no communication has been transmitted. It cannot read it from its own replica because no one writes on X. So it should read from the initial state. Okay? And once you have that, we observe that by the particular construction that we found, the put on X1 is actually visible to the get. Right? You see this green and yellow path. Hence, we observe that the get on X does not read the latest visible value. And that's a contradiction because we expect that instruction should read the latest visible value, and this is not the case. And that's basically the whole idea of the proof. For a general setting, when you have more expressive consistency models, more expressive operations, the proof is essentially the same but more complicated. But the details are in the paper. So let me already conclude with what I show here. The arbitration-free consistency theorem is the first type characterization. It's an if and only, a true if and only if condition of available implementation. And the condition that we found is essentially a syntactic condition. You define your model with the grammar that I presented, then you check the definition, and if it's arbitration-free, you know that it can be implemented, otherwise it can't. But this is not the end. There is more future work. For example, we know that this is the way to check arbitration freeness, but can we automatically check it? Well, that's actually not that trivial, right? Because the definition of the model, taking into account the operation, can be really convoluted. So we don't know yet how to efficiently do it. And another interesting and theoretical question that one could ask is, well, the CAP theorem is a well-known theorem studied in the database courses. And we managed to generalize using this way of thinking. Maybe we can do the same with other well-known results like pass-out or count theorems. Maybe we can get something else out of it. I don't know. We'll see. That's future work. But well, that's all for me. Thank you so much. Happy to have that.
Okay, great. So we have a bunch of time for questions. Does anyone have any questions?
So thanks, great result. I guess my question is a bit high level. So there are other interesting things happening at the level of causal consistency if you compare to stronger and weaker models. For example, you have consistency checks becoming polynomial time. You can also define these models in monadic second-order logic. So I wonder if, for example, one could explore MSO as a specification language for the available systems, or maybe relate arbitration freeness to polynomial time consistency checks. Have you thought about this at all?
For the first part about monadic second order, honestly, I have not thought about it. For the other part about the polynomial checks, yes, but I'm not quite sure if there can be a connection, right? Because I mean, at least the results I know about polynomial consistency do not talk about communication. So I'm not sure how the results apply first in the communication setting. I think that receive before relation is not always modeled in those results. And if they do, maybe there is a relation there, but it depends also on the scope, right? Do we care about communication or not? It's interesting, absolutely sure, but I cannot confirm that there is a link that can be polynomial, if and only if it's arbitration free. I wish for it, but I can't.
Right. It just seems very peculiar that many things start happening, like coinciding at the causal consistency level. So I guess it would make sense to try and look into kind of some unifying theory around that level.
Yeah, it absolutely would be interesting. I wish I could have the answer, but I don't have it yet.
Thank you.
So does the corollary, like, would this actually be an implementation strategy to get or do you think it's too impractical to actually build it around?
I mean, I'm like not sure, right? Because, for example, you can like the first part, like if it's arbitration free, you can implement it. Basically, reduces to implemented causal consistency. So that gives us nothing for anything that is weaker than causal consistency, at least in the part of our result. For anything that is stronger, not so sure, right? Because for example, naive isolation or parallel isolation in the case of databases, they are like efficient ways to, try to overcome this problem. Yet, like in the case of our results, they are group all the category bad implementation. There is no available implementation. So I cannot see why, but maybe there is a way. I just don't know it.
So I have a naive question.
Okay.
In the intro, you said you talk about an example with the booking and the room, and so I'm guessing this does not apply to this example, or if so.
Can you say it again? Sorry.
I'm guessing this was an example where the conditions were not met.
Oh, so sorry. Can you say the whole is a question?
I'm trying to understand so I don't know much about this.
Okay.
I'm trying to understand in practice,
on
the booking example, if you wanted causal consistency to be applied, what would it look like?
And you could have causal consistency on at the end you might, like the case of a booking is a database that uses some SQL operations, and then on top of that you can enforce causal consistency as a model. So you have your operation like SQL, let's say, with causal consistency, and then the application will say SQL with causal, and then you could implement it. Actually, there are real implementations that can enforce those conditions. If that answers your question.
I think so.
Okay, no, we can take it off. Yeah, no, thank you.
Thank you for the great talk. So as far as I understand the results, it relies on these kind of visibility relations for the definitions of the models. But I guess you could define a model like in a more complicated manner that doesn't use these visibility relations. Do you have any feeling of whether the result would generalize to a more general definition of these models?
In its all generality, it will be complicated. I think intuition should still hold in some way, because the drawing is really easy, right? So I expect in some way that it will hold, but of course technically tests can be really complicated. The thing is, the first thing we think, like, which model is used in practice that cannot be defined with this framework. Like, so far for my knowledge that is limited, all the models that different objects can have are already captured here. But maybe there are other interesting models that we cannot capture, and of course, one could think about it.
Okay, so we can take one or two more, but in the meantime, can we have the next speaker come set up? Okay, if there are no more questions, then let's thank Enrico one more time. Okay, so for our next talk, we have Thibaut Perami. He's going to be talking about ArcSem, reusable rigorous semantics of relaxed architectures.
and welcome. So I'm going to talk about ArcSem, which is a ROC framework or library to define the semantics of modern relaxed CPU architecture. So this is joint work with Thomas, Brian, and a few other people here. So first, what is a CPU architecture? So a CPU architecture is the contract, the interface between CPU hardware and the software that runs on top. And so concretely, the hardware must have a limited set of behavior it can have so that the software can rely on this set and be able to function and provide the functionality we expect. So more concretely, the architecture needs to define an envelope of allowed behavior that the hardware can do. And you can think of it in simple terms as a set of final states that are reachable from a given initial state. Or if you want to do more precise definition, you can think about set of allowed execution traces or witnesses. So why do we need such an architecture to be formally defined? First, because formally defining such architecture improves, in general, the definition of architecture for everybody. So right now, the semantics of mainstream CPU architecture are defined in a mix of some formal artifacts and mostly still big prose manual that don't contain all the information. And it's somewhat easy, if you're experienced with this domain, to ask a question that the manual doesn't have an answer for. And so having a formal model allows to close that gap and technically answer all the questions. Furthermore, this allows to do formal proofs about the properties of the architectures. So there were some proofs about Morello cherry extension to ARM that were done in my group. And this work will also show proof about the refinements or abstraction that you can provide with virtual memory on the ARM CPU in a multi-core context. But beyond proving things about the architecture itself, this is really critical for system software verification, so verifying that a given hypervisor or microkernel or something is verified. And so far, all those projects have had to kind of make up their own semantic in the tool that they were working with, because there were no centralized semantic for it. So one of our justifying goals for doing this whole project is trying to improve that state with the verification of PKVM and hypervisor running under Android. But it's still, that verification is very work in progress. In addition, having a formal architecture model allows to go below and prove properties of the hardware. So there was two big examples of verification projects about hardware properties in relation to the architecture specification. And finally, it's also very useful with compiler verification that have had so far the same problem as system software verification in the sense that they made up a semantic of this hardware to suit their needs for their verification project, which is all good. That's what makes the entire project feasible at all. But we would like to improve that state. So how do we achieve a single and all-encompassing architecture model? We need to do this by decomposing into two separate sub-problems. So first, we have the instruction model, which is in some sense simple, but quite big, where you list all the instructions and what they do in terms of what register they read and write, what memory location they will read and write. And this is generally written in ASL and SAIL now. And then below that, you connect that to a memory model that will interpret how those different actions will behave and give you the semantic of the entire CPU with all the multiple threads. And so that's the memory model in some sense is what lifts the instruction model to an entire CPU model. And even at that level, there are still two levels you can do this at. So if you're only interested in compiler or user mode program application verification, you can do a user level model that only is concerned by arithmetic, memory, sometimes but often not mixed size accesses, and it need to do some level of dependency tracking. But if, in addition, you want to verify something like an hypervisor or other system software or even a JIT compiler, then you need to go into the system realms where you have to think about relaxed configuration register, various kind of non-coherent caches, and what are the behavior of exception and interrupts. And this gets really quickly very complicated. So the landscape so far for instruction model is still okay. So the instruction model, to give a bit of a more concrete example, the idea is that you just take a single instruction, you take the opcode, you decode it into an instruction, and then you give the semantics in terms of line of pseudocode. I read that register, I add them together, I write a new register. And so those pseudocode specification are in a decent state right now for mainstream architecture. So ARM actually has an official, quite significant specification of 300,000 lines of code, which is supporting the entire architecture and that they're using internally. And we translate that to Sail, which has a bit more line of code. RISC-V is writing their own specification directly in Sail and is like an order of magnitude smaller. And the Intel state is a bit less nice, but because there is no official specification, but there is an ACL2 specification that is quite decent already, and that's also translated to Sail. So Sail for us is a good target to hook on the back of. On the concurrency model side, what kind of object we are thinking about? So the goal of a concurrency model is to answer a question like, what is the behavior of this concurrent program? And generally, those models are tested with things like this. So litmus test, where you have a few threads, a few instructions in each thread, and you are inquiring whether you can observe a given behavior or not. And there are multiple ways of answering that question. So the natural way would be to take your hardware and simplify it, like still talk about pipeline and caches and buffers, but you simplify it in a way that you can still express the observable behavior while removing most of the implementation details. And that gives you a microarchitectural operational model like the flat model. But you can abstract even more. You can just talk in terms of candidate execution. So you have some sort of multi-core execution traces where each thread does a sequence of events, and then you define relations, a bit like the previous talk, to define what kind of execution are allowed or not. However, in both cases, if you start including all the system aspects I mentioned before, this is becoming increasingly complex. And you start to not be able to handle it by just writing some piece of paper and thinking on a whiteboard, and you need full formalization. And so that's what we decided we wanted for our project, but however, that doesn't really exist, because what we need is a formal architecture model that contains a full ASI model with all the instructions that the software we would want to verify might do. And we want it in an interactive theorem prover, so we can do formal proofs about it and reason about it, not just a test oracle like the existing state of the art. But we still want to execute, because in those tools like Herd of Hyla, there is an insane amount of effort to make the model correct and test and have big test suites. And we want to be able to compare to those test suites to assert that the model we've written in Rock is decent. And so ArcSem is kind of filling the bottom right corner of that table to try to have the best of both worlds, to both support interactive theorem proving and proofs about the model, while still running against real instruction models. So ArcSem, what is it? So the goal is to that we achieved is have a reusable formal framework to define CPU architecture that is architecture generic. So for now, we only support ARM and RISC-V, but I have a student working on the x86 port. It is concurrency model generic, so we have definition in axiomatic and promising model. We are working on operational models, but it is doable. We support multiple instruction models too, and it is useful to support multiple instruction models even for a single architecture, because you want, for example, a user model and a system model that will be at different level of complexity, and maybe you want an even more simplified model to do some proofs and make your life easier in some context. And you still want to be executable, so we also need to do that and be usable to for proof. So how do we do that? So we, again, as I said, to build our full machine model, we combine the instruction and the concurrency model. And the core aspect of ArcSem is defining the interface between those two. So when we started, we wanted to do a generic interface, but in practice, that's not possible. For example, each architecture has a different concept of what are memory barriers. So you do need an interface instantiation for a specific architecture that fills specific customization points, like the type of barriers. And so it's a bit less generic than one could have hoped for. However, we can still do some generic things. In practice, what we've done here is I'll be able to ingest into our framework those three instruction models. So we import the full 400,000 line of the ARM model. Same for the official RISC-V model, and we also have a small ARM model for testing that is of the order of 10,000 line now. On the concurrency side, we've mostly focused on ARM so far. So for ARM, we have a simple user axiomatic model, a mixed-sized one, a virtual memory model, and we also have a user promising. And we are working on a VM promising, but that's not existing state-of-the-art, so we are working on it. For RISC-V, we only have the official model in the manual, and then we can also define simple testing models like a sequential model, and it still works well with our framework. So how do we connect those two pieces? So our interface from Sail is divided into two components. So from the Sail model, you extract both the interface instantiations themselves, so the red bits from the previous slide, so the types of barrier, for example, that you need to instantiate your interface, and you also extract the behavior of instructions that are two separate components. And the first one is a module in Rock, so the whole framework is parameterized by that module, so you instantiate the whole framework that allows you to define the interface, write concurrency model, and then concurrency models end up having a shape of a function from the instruction behavior to a full machine model. And so then it's just a Rock application. So slightly more concretely, but still very simplified, the shape of the interface is as a set of algebraic effects. So if you think about your instruction pseudocode, it will do memory read and write. But when you write your pseudocode, you don't really need the actual semantics of what reading and writing memory is at that stage. You can delete that to your concurrency model and keep reading and writing memory as algebraic effect. Same for barrier, same for register access, and same for many other effects. We have on the order of 15 effects right now in ArcSem. And once you have those effects defined once in the sales center library, you can define instruction model. So first you need to instantiate the interface, define all the registers with their type, and then you need to instantiate specific types, for example, the barrier type with one concrete enumeration, for example. And then you can write the code of individual instructions. For example, this load instruction can be written with like 5 lines of just reading a couple of registers, computing the address, doing the load, etc. Then we need to lower that into Rock to be able to do proofs about it. So first, in Rock, we define, again, the set of algebraic effects formally. And we use the free monad on top of this set of effects to represent the semantic of arbitrary effectful program over this set of effects. And this allows us to express in Rock the semantic of our instructions. And then the other 2 bits can be translated automatically by Sail into Rock. So first, Sail will translate all the interface instantiation parameters into a single Rock module that can then, we can then apply our framework on. And then it will translate the semantic of individual instruction code in Rock monadic code. So we use the free monad in Rock with the usual monadic binds, etc. And then this second object can be consumed by concurrency model. So if you write an operational style model, you will just write an effect interpreter. So you will just interpret effects in some state that can be more or less complicated depending on your concurrency model. And if you are more of an axiomatic style, so you only care about traces, then your free monad will generate a set of allowed traces for a single specific instruction. And then you can define the traces of many instruction program with multiple core as a combination of those single instruction traces. I'll try to make it slightly more concrete with an example of a simple instruction on a simple sequential model. So if you take a load instruction, so you're reading address in x0 and writing back to x1, the code is quite simple. I mean, heavily simplified compared to the reality, of course. Translated to Rock, it would be basically the same thing, but with some monadic bind and some more explicit register effects. And then when you run that against a sequential model, you just start from some initial state of your machine, and then it's quite standard communication. So you issue one effect, the sequential model processes it and returns the value in its state. Then you issue another effect, you get the value that is in state again. And for mutation, you just issue a write effect, and the state is mutated, and then you return unit. So when you're running against a simple sequential model, all of this is quite standard. When you're running against more complicated concurrency model, of course, it is not that simple. So we found that in practice, the free monad is actually a very good representation for our instruction model, because a single instruction can really be thought as an effectful program over those uninterpreted effects. And in addition, a single instruction is always terminating. A single instruction cannot diverge. So we do not need iterates or more complicated co-inductive data structure for it. A free monad is good enough. However, there are some drawbacks with this. First, real architecture do need non-determinism, which can be somewhat alleviated by adding a choice effect, but then there are some limitations around what you can actually realistically execute if you want an exhaustive exploration of your state space. Then you also have a problem of failure and undefined behavior. An instruction model might be partial, might need to crash and catch fire. And so here the problem is not so much representing it in the interface, you can just add a fail effect, but that currently none of the concurrency model of the literature actually supports the instruction model failing. So that's another whole kind of worm that needs to be solved. And finally, currently, the free monad doesn't support doing multiple effects in parallel. So if you have an instruction that does 2 memory accesses, it might want to do 2 memory accesses and not wait for the reply of one before issuing the other. And the free monad data structure does not allow that. So we have a plan to extend the free monad to support parallelism, but it is not implemented in Rock yet. which means that the current ROC implementation does support most instructions that you would use in litmus test and most code, because all those instructions like plain load and store, plain arithmetic instruction can be expressed as a linear sequence of effect. But some more complicated instructions like compare and swap or multiple memory access instruction cannot yet be fully represented in all their parallelism. So if you do a sequential execution, you will get the behavior, but it will be too linearized compared to what the architecture wants. And so this free monad allows really to decompose the reasoning between instruction model and concurrency model, where you can do proof about your instruction model without having to think about the interpretation of the effect, just as traces of effects. And on the other hand, you can do proofs about concurrency model by just universally quantifying of all the free monad values, maybe with some side condition. And this is a quite powerful proof technique. And finally, so for the overview, for the concurrency side, you can relatively easily implement the usual style of models with this setup. So for axiomatic model, you just take the set of traces generated by your free monad, you glue them together for an entire thread, and you glue them together horizontally for all your threads, and that gives you the usual graph that you want to write relations on, define well-formedness, define your axiom, and you can define your model that way. And if you want to be on the operational side, then you actually use the operationalness of the free monad. So you define it as an interpreter over some state that you define, and then you can define your transition and your model. All of this can be used to do proofs. So there was a paper by me and other people, I'm not first author, 2 years ago in POPL of a program logic in Iris based on a previous version of this framework that allowed to prove programs over such a very relaxed architecture model. And we can prove like a spin lock on some other example using Iris. And then we did some proofs in this work about relation between models themselves. So to check that we can relate operational and axiomatic model, we did do some simple proof that the sequential model is indeed sound with some axiomatic model on a single thread. But the main course of the paper is a VM refinement theorem. So what do I mean by that? I mean proving that the abstraction that an operating system can provide to a user mode program through virtual memory is sound. So when you read the ARM manual, you will have two sections. You will have the user section, how people should program application in ARM, and you will have the system section, how people should program operating system in ARM. And it is very important that people in the second section that write an operating system can configure the architecture in such a way that they can launch user mode application that indeed provide the model that the architecture pretends it is. And in some sense, it's kind of a pretend, because the first part, the user mode application, is not just the job of the CPU to program. It is a combination of the CPU and the operating system that has to provide this abstraction. And so what this theorem answers is that it is possible for an operating system to provide that abstraction. So if you configure the architecture in some way, and then you run in user mode, then you will behave as if you were in the user mode application model. So yeah, so that's what the first very cartoon version says, like you can provide the architecture to provide the abstraction you want. And a slightly less cartoon statement is that if you start in user mode with a specific configuration that has page table and registered configured according to some sensible assumption, the page table don't map themselves, so the user mode program can't modify its own configuration. Then any execution that stays in user mode, so doesn't does a syscall or raise an exception, that is allowed by the full complicated model that contains translation and concurrency about TLB management and caches, can also be allowed by the regular user mode model, where the instruction model doesn't contain translation anymore, and the concurrency model is the usual user mode model. And this ensures that if you do reasoning on your user mode program against this simple model, it will be sound even in running on a full CPU with a system, on an operating system under you that has configured the page table properly. And so in order to achieve this proof, having the decomposition of instruction versus concurrency is very important, because first we could offload proofs about the instruction model to Isabelle, where there is already a quite decent piece of infrastructure that we didn't want to reinvent in ROC. So the Isabelle version of ArcSem doesn't have concurrency at all. It has a free monad, and it talks about single instruction traces, and it never thinks about anything more than a single instruction. But it does handle the 400,000 line of the ARM specification, which turn into 1 million line of Isabelle. And so that proof is quite big. So there is 50,000 line of automatically generated Isabelle proof, but another 10,000 line of manually written proof. And those can prove properties of the single instruction architecture, like before any memory access, there will be a translation and other similar properties. And once that's done in Isabelle, we can decompose the proof above entire model into 2 steps, where we can lower separately the concurrency model while keeping the instruction model abstract and unchanged. And then in a second separate step, we can lower the instruction model to user mode while keeping the concurrency model unchanged. And so the complicated reasoning about moving from a concurrency model to another was formally proven in ROC. And the second step is a quite simple gluing of the Isabelle proof and some relatively simple graph reasoning. So we did that in paper mass. So what does that leave us? There are still some issues to solve, but this is already quite a decent piece of work. So first, partiality. As I said, none of the concurrency model right now currently correctly handle undefined behavior. They don't define their own bounds. So if you have a concurrency model for a CPU in a paper, they will say this concurrency model talks about that, and that feature. Then they give you a model. But the maths of the model itself doesn't know what its own limit. So if you start it on an initial state that doesn't satisfy what the prose next to the model says was supported, the model will just give you a garbage answer. And you don't have a way of mathematically defining what are the limits. So that's something that needs to be fixed. Second, we do need to implement our plan for supporting an extension of Fremona that allows doing multiple effects in parallel. And then we do need more testing. So right now we are testing a couple of litmus tests, but we need to run full test campaign against the existing state of the art. Intel support is in progress, and then of course we can arbitrarily do more models, more proof about any of this. And if you're interested, this is also very interesting to use for any other project that talks about architectures, either below or above. Thank you for your attention.
A few questions.
So what's so complicated with x86?
Oh, it's not that complicated. It's actually
CSO plus things.
In some sense, x86 is simpler than ARM. So that's mostly why we focused on ARM first. It's not that we haven't done x86 because it's hard. We just haven't done it because we started with ARM and we haven't had the time. But I'm asking a bachelor student to do the x86 part of the thing. So it's just we haven't had time to do x86 yet.
Yeah, thanks for the talk. Really interesting. So you motivated it at the beginning with also wanting to have executable semantics so that you can simulate things. How do you deal with these axiomatic models, which in the end just give you a predicate about, right? Like if you compose with an axiomatic model, in the end, you cannot start partially executing your semantics. You have to know everything in advance.
Yeah, so that part isn't solved right now. We can only execute operational models. It is solvable by basically having some kind of generator that will generate set of interesting traces, and then proving that basically there are some obvious rules you can do to remove vast range of useless traces, and then only some are really interesting to run the full predicate on. So right now our status is that given a trace, we can compute whether it's okay or not, but we haven't done the generator yet.
Hi, thanks for the talk. I guess one question I had, I guess it's not really commercially relevant anymore, but would the approach that you've taken work well with like even weaker memory models like you saw in like Alpha, which doesn't have any kind of like data dependency ordering or anything like that?
We think so, but we haven't actually actively tried to do it. But there is nothing in this framework that requires like multi-copy atomicity or anything like that.
Okay, cool.
So in theory, you can do whatever.
Thank you.
Okay, so we can take one or two more while the next speaker sets up.
Yeah, thanks for the talk. I'm curious about the pen and paper gap that you are. The gap between the two proof assistants that you're filling with pen and paper arguments. So what is your long-term strategy for that? Will it stay like this and you continue developments in different proof assistants?
So the thing is that the infrastructure that was developed in Isabelle to do that proof was 2-year person. So we have emitted the idea of porting it to Rock, but porting a project that scale is not really research, so I'm not sure we'll have the manpower to do it. But we are relatively happy with that setup because the interface itself is quite small. Like there is only like 15-ish effects, and the free-monad structure is really the same on both sides. So I'm not sure it's a problem that we are going to immediately solve. Maybe we will do new proofs about instruction set architecture in Rock if we can. But then Rock has way more difficulty than Isabelle to scale to those sizes. So yeah, there is no silver bullet here.
Thanks.
Okay, let's thank Thibaut one more time. So for our next talk, we have Dvora Chait-Roth, who's going to be presenting consistent updates for scalable microservices.
Okay. Hello, everyone. I'm Dvora. I'm a PhD student at NYU. This is work that I did with Kedar from Nokia Bell Labs and my advisor, Thomas. And we're going to talk about consistent updates for scalable microservices. Now, this work is about live updates. So that's an update that you apply to a system while the system is still running. And when you do a live update, you can enter into a state that we call mixed mode, where you have an old version and a new version worker concurrently active. It's a mixture of the two. Now, when you have two versions active at the same time, that can lead to all sorts of errors. So what we do is we propose a way to guarantee that even when your system is in mixed mode, it still behaves consistently, meaning it still looks like it only has one active version, even though really it has two. OK, that's the first half of this title, but first let's talk about the setting of scalable microservices. We're going to use a basic messaging service as an example, like WhatsApp. In a microservice, you have a set of clients who send requests to workers, so like send a WhatsApp message. The servicing worker will operate on a shared data store, so put that WhatsApp message in the recipient's inbox, and then send some kind of response back to the client. Now, the full functionality of the service is contained in the workers. And at some point, you're going to want to update your functionality. Now, assuming that your new version is not buggy, we want to know, how do you update from the old version to the new one? OK, so a very easy way to do this is what we call an atomic update. You'll just shut your whole system down. You update all of your workers together atomically, and then you bring everyone back up. But if you have an online service that can't be shut down, then updates become not simple. And these are live updates. You're updating your system while it's still running. Now, how can you possibly do that? It sounds like changing the tire of a car while you're still driving. I do recommend this video. Now, now, how do people pull this off for live updates? Well, one way is you can use duplication. So you can just make a whole new set of workers that are updated. And then when that set is ready, you switch your traffic over. But this has the downside of you need to duplicate all of your workers. Instead, you could do something kind of simple called a rolling update. And you just go worker by worker, updating your workers, and whoever is not being updated is available. So why would you ever use extra resources to do like a duplication style update? Because while you're updating, you have a mix of versions active at the same time. We have old and new version workers, both servicing clients, both accessing the same data store. And this is what we call mixed mode. Your service is not the old version. It's not the new version. It's a mixture of the two. And that is very dangerous. Now, to demonstrate why, let's go back to our WhatsApp service. So let's say that we're updating WhatsApp so that it automatically translates a message to the recipient's native language. OK, so we have Bob in America and Claire in France. And Bob sends a message to Claire in English. And we're doing a rolling update. It's mixed mode. So his message gets routed to a new version worker. So as per the update, it will automatically translate that and puts the translated version in Claire's inbox. OK, now Claire reads that message. And she says, oh, it's an updated system. I'll send a message back to Bob in French, and the system will take care of that for me. But we're in mixed mode, and her message can be routed to a non-updated worker. It doesn't translate the message. And being American, Bob does not know what the message says. Now, this is a very lighthearted example, but it's had very, very real bad consequences. In 2012, a trading company called Knight Capital went bankrupt in mixed mode. A message meant for a new version worker went to an old version one, and that triggered an infinite cycle of trades, and that bankrupted the company. And the problem has not gone away. The AWS outage in October was a type of mixed mode. You had old and new DNS configurations that were active at the same time. And the Cloudflare outage in November took so long to fix because the system, it was a rolling update, it was in mixed mode, and their diagnosis software could not address the bug in mixed mode. In SOSP 2021, this study examined over 100 real-world update failures. And they found that 63% of these were caused by cross-version interactions, by this mixed mode state, and 2/3 of those were catastrophic. So this is a real problem. What has been done about it? There's work on resource duplication, but that's like just an expensive way of avoiding mixed mode. It's not addressing mixed mode. There's work on type safety and preserving invariants, but type safety does not protect you from mixed mode, and writing good invariants is hard and system specific. And there's work on the setting of network updates, but it's a little bit too restricted to really address our problem because there's no data store, and the only updates that you can do are changes to path configurations. Really what we're missing is a generalized idea of update consistency and formal foundations for us to reason about mixed mode updates. But without this, we can't really prove anything at all. And this is where our contribution lies. We give the first formal reasoning framework for mixed mode updates, a definition of update consistency, an inductive proof method for update consistency, and algorithms for consistent mixed mode updates, which we prove consistent using our inductive proof method. Hooray. Now, everything that we did is built on our definition of update consistency. So before we get too formal and people start to space out, I want to give an intuition here. And for this, let's return to our problem. Now, what went wrong here? It's very, very tempting to say what went wrong is that we are in mixed mode, because we know that the system works well in the old version. And we know that the system works well just the new version. When we're in mixed mode, that's when things go wrong. And it's true, that's when things go wrong. But being in mixed mode isn't actually the problem. We want to be in mixed mode. We want to do these rolling updates. The problem is that our clients saw that the system was in mixed mode. They experienced the effects of mixed mode. But if clients don't see the mixture, if to them it just looks like the system updated atomically, then we know that the internal inconsistency has no effect. And this is our definition of update consistency. To every client, it looks like you did an atomic update. Because then we know that the behavior of the system is indistinguishable from this clean switch. You're not experiencing the effects of mixed mode. Now, I want to say this is a conservative definition, because there might be specific cases where clients can see that you're in mixed mode and nothing terrible happens. But we want a standard that's going to ensure that regardless of your system, regardless of your update, you don't experience mixed mode failures. And with this definition of update consistency, we can design consistent mixed mode update algorithms. And we use an update manager. It's sort of like a scheduler component that's going to intercept all of the requests coming in. It will inspect the properties of these requests, and it will very cleverly decide whether to send your request to a non-updated or an updated worker in such a way that it will ensure that no client sees the mixed mode behavior, that to every client it looks like an atomic update. And with our formal foundations, we developed a proof method for showing that our update algorithms are indeed consistent. Okay, now if you want to go to sleep, you can. We're going to make everything more formal. So first I want to talk about two important assumptions that we're making on our system. One is it's a black box to clients. They don't know the particular actions that the workers and the data store are taking. And similarly, clients are mutually independent. They don't know what requests and responses other clients are getting, right? All anyone sees is their own requests and responses. Now, we represent every single one of these processes as a transition system with FIFO channels between clients and workers in the data store. And the behavior of the system is traces over an alphabet of send and receive events. Now, in the paper, we really deal with computations. We're concerned with states also, but for the talk, we're just going to focus on actions. Now, workers are the only processes that are being updated here. But when workers communicate with clients and with the data store, that communication is going to be impacted by the version of the worker. So we mark all communication with updated workers as updated, and everything communicating with non-updated workers as non-updated. And now we can build a trace that is coded by version for every single action, for every single process's actions. Now, this is an atomic update because we can see that there's one point where the whole system switches over all at once atomically. Now, in contrast, this trace shows a mixed mode update. You have that mixture of versions active. And in order to show that a mixed mode update is consistent, there has to be an atomic update that is client equivalent to it, meaning equivalent in terms of client observations, because that's really what we care about. Even though the trace is recording the full message passing of the entire system, clients are seeing this very restricted view. So if we start with a mixed mode trace and we just project out the client observations, then there's like a whole world of other traces that are equivalent to that on the client observations. And if one of those has an atomic update, then we know that our mixed mode update is indistinguishable from an atomic one from the client's perspective. And this is our formal definition of update consistency. A trace row is update consistent if for every client C, so fix a client C, and there exists a trace with an atomic update that is C equivalent for that client to your original trace. And I want to emphasize here that this is a for all exists property. It's not exists for all. So this perceived atomic update point can differ from client to client. So Alice can say, oh, there's an atomic update at this point, and Bob could think that the system is still non-updated there, and he sees an atomic update later. All that matters is that every single client perceives an atomic update. Now, if we want to prove update consistency, how can we find an equivalent atomic trace? So one method that we use is commutativity. So let's say we have Alice sending Bob a message via an updated worker. So that gets stored in Bob's inbox. And then Bob sends a message to Claire with a non-updated worker, and that gets stored too. Now, from every client's perspective, this looks identical to if we switched the order of the non-updated and the updated actions. And this has an atomic update. So in other words, we're using commutativity to find equivalent atomic update traces. And this is the basis of our commutativity algorithm. Inputs which actions are commutative from their system. And the update manager is going to ensure that all of the requests are directed in such a way that if you ever have a non-updated action, it's left commutative. You could push it to the left of all the prior updated actions so that you have that atomic update. Now, all that really matters for our algorithms is the version of a worker. So we could just collapse everything here, just old or new. That's all that matters. And the first request, it doesn't matter where it goes because there's nothing to compare it against. But once that next request comes in during your rolling update, the update manager is going to inspect the semantic properties of that request. And it's going to ask itself, if this was sent to an old version worker, does it commute left? Now, if it does, that means that from the client's perspective, they'll perceive an atomic update. They'll see old and then new. And then it has the freedom to send it to an old version worker, or it could send it to a new version worker too. It has that ability, but now it could send it to either one. If the request is not commutative, then the clients will see, oh, this is not an atomic update. I see updated actions and then non-updated ones. So in that case, the update manager is forced to send it to a new version worker so that we make sure that clients don't see that internal inconsistency. Now, it might sound sort of obvious to use commutativity as a way to find these equivalent traces, but the proof that this algorithm is correct actually turns out to be sort of tricky. So let's talk for a second about how we reason about consistency of these algorithms. Now, what do we want to actually do? To prove correctness of an algorithm, we have to show that any trace that's produced by this algorithm has a client equivalent trace with an atomic update for every client. So first of all, for the purposes of our proofs, we switch our trace model. We've been talking in terms of interleavings, which are very nice and intuitive, but interleavings are a little bit too strict. They enforce an ordering on actions that are actually concurrent, that are not ordered. So for our proofs, we switch to a partial order model using Lamport happens before relation. So every process has a timeline that orders actions, and then actions are also ordered by sends and receives between different processes. And something that we're going to use for our proofs is called a consistent cut. Now, a consistent cut is a way to pinpoint a moment in time across distributed processes. So you collect actions from each process, and now if that is downwards closed, if the set that you have includes everything that happened before it, that's a way to express a point in time. So for example, if I want to pinpoint all of the non-updated actions, that last moment of non-updated, then I'll start here with C1's non-updated receive, and I'll work my way down the chain so that it's downwards closed. And here we go. This cut is a point in time. Now, if we have an atomic update in the partial order model, what that means is we should be able to create a consistent cut that has all of the old actions on one side and all of the new ones on the other. There should be a moment where everything switches. And this is not a consistent cut. We have updated actions in this moment in time, really concurrent with or before our non-updated actions. But if we look at this pair on the data store timeline, and we commute the old before the new, and now we build our cut again, those actions that were previously in the cut are now outside of the cut. And we have that atomic update, that clean divide between old actions and new ones. And this is what our commutativity algorithm is allowing us to do. It's guaranteeing that we can make these swaps until we get that clean divide. And a little more formally, we have an inductive proof method that's going to show that we can keep making these switches. Now, the proof method is really a classic ranking argument. So for that, we need a progress measure, or otherwise known as a ranking function, something to measure how close is a given trace to having an atomic update. And we build this progress measure so that an atomic update has measure 0. And now the argument, the proof method, is you have to show that you can keep making these, you can keep rewriting your trace in a way that's client equivalent, that makes progress, that decreases your progress measure. And once you show that, you'll be able to decrease, decrease, decrease until you get to this atomic update measure 0. And now, what is this progress measure? I'll talk for a second about that. Intuitively, you could try to count the number of blue actions inside the cut, right? You want that clean divide. The blue actions are out of place. But this is actually a little bit not sensitive enough. It really only cares about changes that happen at the border. So if we have this example, we have 3 blue actions outside the cut. And now we do the same thing that we did, right? We switch the old before the new. Intuitively, that should bring us a little bit closer. But that wasn't at the edge, so there are still the 3 same actions inside the cut. So we wanted something a little different. So we can try to count the number of inversions. This is like a classic way to count, to measure sortedness. So how many pairs of new before old, how many things happen out of order. But this is also insufficient. And to show why, I'll give you a little glimpse of our other method for finding equivalent atomic traces, which is using backwards and forwards compatibility. Now, in brief, backwards compatibility is a way for a blue action to look red. For a new action, an action done by a new version worker, it looks like it was done by an old version worker. And forwards compatibility does the opposite. A red action can look blue. Something done by an old version worker looks like it was done by a new version one. And if we have a trace, so we really measure sortedness on the data store. I could talk about that offline. But if we have this data store timeline, and this action here is backwards compatible, so that means that it's equivalent to one where the blue action is red. And we count the number of inversions. So on the original timeline, we have this inversion over here that we don't have in the equivalent one, but we gained 2. And that shouldn't be happening either, right? Intuitively, this equivalent one is also closer to an atomic update. Now, very nicely, it turns out that if you take the ordered pair of the 2, the cut measure and the inversions, that works quite nicely. I invite you to see more details in the paper. But before I finish, I want to talk about our impossibility result. Now, in our algorithms, the update manager has to do this very important step. It has to look at the semantic properties of each request coming in. And that's sort of less than ideal, right? Examining requests takes work. We want an update manager that's oblivious to the requests coming in, that sends them, it chooses how to direct the requests regardless of what the particular requests are. Now, let's think about the properties that we're aiming for over here. We're aiming for an update algorithm that's oblivious, that directs things the same regardless of the semantics of the requests, that runs in mixed mode, and of course, that's update consistent. And if we think about the techniques that we've seen, a duplication update is oblivious. It does the same thing. You duplicate your workers no matter what your system is. And it's update consistent. It has that clean switch, but it's not in mixed mode. A rolling update is oblivious and it runs in mixed mode, but it's not update consistent. And our algorithms are update consistent and they run in mixed mode, but as we said, they're not oblivious. And we want to know, can we fill this middle section of this Venn diagram? And we show that that is impossible. You cannot have an update algorithm that simultaneously is oblivious, runs in mixed mode, and is update consistent. So in other words, we give semantics-based update algorithms for mixed mode, and that is the best that you can do. You can't have an oblivious algorithm here. Now, to sum up, we gave the first formal reasoning framework for mixed mode updates, a definition of update consistency, an inductive proof method for update consistency, and algorithms for consistent mixed mode updates. And I hope that I've inspired you to read the paper and learn more about this, because it's really just the beginning of our exploring this topic. We're thinking about, what if we're updating the data store? What if clients need to update? Or, how do you make this all more realistic? Usually it's not just one microservice. It's a whole network of microservices now. The microservices themselves are clients. And so there's really a lot to explore over here. And I invite you to read the paper, come talk to me. And thanks to these artists who provided all of these great graphics. Yeah, thank you very much.
Great. Looks like we have a question over here.
Hello, thank you for the talk. My question is about availability, where it seemed that perhaps one of the reasons for having multiple workers that you can query them in parallel, and well, if one fails, you can still communicate with the others. But now you're putting something which mediates the interaction with the workers. So now, how do you have availability? That's the question.
Okay, so usually when you have like a microservice structure like this, there is like a load balancer component. There usually is something in between the clients and the workers, but that is much less intrusive than the update manager. So you're asking a fair question, like how much does the update manager slow things down, right? And we're hoping to implement, this is like some of our next steps, is sort of how do you implement this system and get like some time bounds on how bad the update manager is. Yeah.
So perhaps a different, similar question is, do you have replicas, or do you replicate the algorithm manager, the update manager?
So that is a way to do it, but then you're going to have to, okay, so the bad part about this update algorithm that I sort of slid right past is that you need to have, you have ordering requirements. You need to, if you want commutativity, you need to know what came before. And you don't exactly know that at the point that the requests are coming into the update manager because the workers are all operating in parallel. So we have to impose some kinds of ordering constraints. And that would get a little bit tricky with multiple update managers, and we need some kind of, I guess, a consensus program, something to deal with that. But would love to talk about that more because that's something that we're exploring. Yeah.
So thanks for the super clear and interesting talk. I have a definitional question. So the definition of update consistency that you gave universally quantifies over the view of every individual client. And one could imagine other definitions too, where you think about groups of clients. I'm curious if you guys have thought about why your choice is the right one, or what the trade-offs associated with that choice are.
Yeah. So what we gain from each client being individual, well, let me say it a little differently. Once you have groups of clients, you can sort of change your setting to be, instead of the clients being sequential, meaning in our model, each client sends a request and waits for a response. If you have groups of clients that are sort of, let's say, communicating with each other, so now they're sharing that knowledge. Now that you could model that as just a single client sending concurrent requests. right? They send a request and get response back. And we actually started with that, but found this to be a simpler setting to build the foundations. But the individual ones really amounts to this separation of knowledge between each individual client.
Okay, great. We can take one more, but in the meantime, can we have the last speaker come set up?
With your definition of input consistency, I feel like the old workers could get overworked pretty easily. Do you have an intuition, maybe even a formal proof or something that they're not too overworked?
Okay, so that's a really good question. Something that we're playing with right now is sort of you can look at the properties of your system. With all their algorithms, there could be an overworking on the updated workers. So depending on the properties of your system, like how many requests are commutative, you can be clever about the pattern that you use to update your workers. So if a lot of things are not commutative, and now let's say your updated workers are going to be working a lot, so you're going to want to make sure that when you start that update, you have a nice amount of updated workers. But you definitely playing with the way that you update the workers is going to be important in efficiency. Yeah, thanks.
Okay, let's thank Devorah one more time. All right, now we have the last talk of this session. We have Thomas Haas. He's going to present recurrent sets for proving fair non-termination under axiomatic memory consistency models.
Okay, thank you for the introduction. My name is Thomas Haas, and this is joint work with Roland Meyer, Hernan Ponce de Leon, and Andres Lomelli Garduño. And what we want to look at is how do we prove non-termination of concurrent programs running under weak memory. And by weak memory, I mean, say your CPU can reorder accesses, or like out-of-order execution, or has a store buffer, all of which may affect the semantics of your program. Now, we also want to consider certain fairness assumptions of our system, but this is something I will omit in this talk, so I will focus mostly on the weak memory aspect. And what I explicitly do not want to do is prove termination. So we are focusing on non-termination, not proving termination. Okay? Now, with that cleared up, the question is now, what is a suitable proof object to show non-termination, to witness non-termination? And there is an answer to that, namely recurrent sets, well, at least in a sequential setting. So let's look at those. Here you see a state space, and a recurrent set is basically a subset of the state space, and it satisfies two properties. The first property is that we can reach it from the initial state. And the second property is that we can stay inside this region. Okay? And if you find such a set, then it's very easy to see that it induces a non-terminating run of your system. By property 1, we can reach the blue region. By property 2, we can forever stay inside. Now, there's actually a theorem that says your program is non-terminating if and only if such a recurrent set exists. The problem with that theorem, however, is that it works over this classical notion of state, and it doesn't support concurrency, in particular, no weak concurrency. It does not have any notion of fairness, well, because there's no concurrency to begin with. And it works over an operational semantics. And now you might be wondering, what's the issue with an operational semantics? So let me tell you. An operational semantics works over states and transitions. And it has turned out that states and transitions are not the best way to model weak memory. And as you have seen in the previous talks, people like to use this kind of graph representation instead. So what we want to do is we want to have a semantics, or we want to use axiomatic semantics over execution graphs instead, because they're very suitable to model weak memory behaviors. What do I mean by that? Well, let's look at this simple program here. You don't need to understand the details, but we have two threads that want to enter a critical section. And to do so, they first signal that they want to enter it by setting some flag to 1. The first thread sets F to 1. The second one sets G to 1. But in case both want to enter, there's a turn variable that decides who gets priority, who is allowed to enter. Now, the program itself is not so interesting, but the important part is that we can understand behaviors of this program in the form of execution graphs. On the right-hand side, you see one execution graph. And the nodes of this graph that I call events essentially amount to read and write operations performed in the code. And then there are edges between those that somehow, between these events that show the interaction of these events. There's the program order, the black edges, which just amount to the syntactical order in the code. So just the order in which these write and read operations were written down in the code. The second one here is the reads from relation, the green edges that just say, where does the read operation take its value from? What store, what write did it observe? And the last one is the coherence order, which says, well, if I have multiple writes on the same location, in what order do they overwrite each other? What is the order in which they hit the main memory, so to speak? Okay, now why are these graphs so interesting? Because once you have a graph, you can just throw it into a memory consistency model or short memory model for different architectures, and these memory models will tell you if this graph describes the valid behavior of the system or not. For example, this graph does not describe a valid behavior of sequential consistency, but it could describe a valid behavior under, say, an ARM architecture. So an ARM CPU that was executing this Patterson code would be able to show this behavior. Okay. So how do we get from these states and transitions to execution graphs, and what is even the analogy of transitions on an execution graph? The idea is, well, we do it in 2 steps. The first one is we go to a different operational semantics that works over runs instead of states. What do I mean by that? You see a state. States are simple. They have transitions. And when they do a transition, they forget about where they came from. You just know about the target state. But if you simply keep track of the whole states you run through, you get a run. And runs sort of they simply capture more information, right, about the system. And it's very easy actually to lift state-based notions like invariance or recurrent sets up to runs. So instead of having a set of states closed under transitions, you can have a set of runs closed under extensions of runs, okay? Now, from these runs, it's not so difficult to go even further to execution graphs, because execution graphs are essentially runs, but partially ordered. And this idea of extending them is the same as extending runs. We just append stuff to the end. And with that, I want to present the first contribution, namely execution-based recurrent sets. And when I say execution, I mean execution graphs, but I will shorten it to simply execution, okay? Now, what does it look like? If we take this state space here and of the original picture, the first step is to replace states by execution graphs. So we get an execution space where the dots are now graphs, execution graphs. And instead of transitioning between states, we now extend graphs. We replace transitions by extensions. We append stuff to the graph. And we can now basically reuse the same definition of a recurrent set. It must be reachable. There must be some graph inside that can be actually produced. And these graphs can extend to other graphs inside this region. Now, this fairly keyword in there. As I said, I will omit fairness in this talk, so just ignore it, okay? But we can give a theorem that says a program is fairly non-terminating under some memory model and under some fairness assumptions, if and only if a recurrent set exists of this shape, okay? Actually, there's a slight side condition. The memory model has to be nice. I will come to this in a moment. But fortunately, all memory models are nice, so it's a non-issue. Okay, so let me demonstrate this. Here we have a snippet of the Patterson, of an execution graph corresponding to Patterson's algorithm. And both threads want to enter the critical section. They have set their flag to 1. But these, as you see, due to the red edge, the coherence edge here, the second guy has set the turn to 1. So actually, the first thread is the one who gets priority, who should enter the critical section. Now, we take this graph as our initial graph to form a recurrent set. And now let's say the first thread we extend it. It observes the variable g. Say it observes the value 0. It doesn't really matter. But we can extend it, and this will be our second graph. And let's say the second thread now performs its loop iteration. It checks if it can enter the critical section, okay? It observes that the first thread wants to enter, f is 1, saying the first one wants to enter, but it also observes that the turn variable is 1, so the first one has priority to enter, meaning the second guy cannot enter its critical section. Okay, great. So this will be our next graph. And let's say we have an unfair scheduler, a scheduler that does not schedule the first thread anymore. Then the second thread will just repeat its loop and observe the same situation again, okay? And we can keep on doing this and get the graph bigger and bigger and bigger, and we get sort of a sequence of graphs. And it turns out that this sequence of graphs converges to an infinite graph. And we can prove that this graph is both fair with respect to some fairness notion, and well, in this case, unfair, because the scheduler is unfair. And it is consistent with the memory model. And actually, to make this conclusion that it's consistent, this is where niceness is needed. Niceness is basically a continuity property. We have to somehow, because the finite graphs are consistent, we have to conclude from the finite snippets to the consistency of the infinite graph in the limit. So this is a continuity property. Okay, great. So now we have seen recurrent sets. How about using them in practice? Well, recurrent sets are great because they can characterize fair non-termination, but they are also very bad in the sense that they lack finite representation, because they now have to be infinitely big, because they have to contain bigger and bigger and bigger graphs. Now, we want to tackle this issue, and how do we get finite representations? It's always the same answer: we apply abstraction. Now, the question is, what is a suitable abstraction for graphs? And the answer is, well, we don't know usually. I don't know. But let's make a question a bit easier and think about runs again, linear runs, not partially ordered ones. And a very good abstraction for runs are states. So we go back to states now. Let me explain. You see, a run is basically a state with some history. It has a very concrete past that ends in some state. And if we just forget about the past, where we came from, well, then we are left with a state, right? So the state that we're left with is an abstraction of all the runs that lead to the state. So basically, a state is actually an abstract past, and we can even see the state as a very concrete infix of the original run. So it's not just a state, but it's a particular small run that is a subsequence of the original run, so to speak. Now we can also look at what are the possible futures that the run could go to or the state could lead to. And I call them past compatible futures. Now you might be wondering, what does it even mean? And are all futures compatible with the past? Yes, they are. That's the point of operational semantics. We don't care about the past at all. But keep this in mind for a moment, because we want to make these two observations here. First, a state is basically nothing but a concrete infix of a run, plus some abstract past. And this sort of run to state abstraction I've shown you actually loses no information about the future at all. It's very precise with respect to the futures of the system. It only abstracts the past. Now, the first point is great because this idea can be readily applied to executions. What do I mean by that? Just replace run infix by graph infix and you're done. Just take an infix of a graph. The second one, however, will fail on executions because executions, due to the way they capture reordering, something that happened in the past could have been reordered to the front and then still be observable in some sense. So the past is not really the past due to reordering in some sense. What actually happens is that we will lose, our abstraction will lose futures. However, this will not be a big problem because all we care about is a single future that is able to witness non-termination. Okay? So if you go back to this picture here, we basically replace the states now by graphs, but graph infixes, so think of a small graph. And we somehow abstract the past. Maybe we don't throw it away entirely, but we somehow abstract it. And what will happen is that now the futures that we are sure, so the futures before the abstraction, there was a set of possible futures. This will get now smaller. in the sense that we are not sure if all the previous futures are still compatible with all the paths that we've thrown away, basically, or that we got through the abstraction. But as long as the set is not an empty, this is fine for us. So let me demonstrate this. Here, again, we look at the Patterson example. And the first thing we do now is, instead of extending this graph, we abstract something. We put a black box over some of the events of the past, and all we keep in mind, all that we remember is the values that the past was able to produce, or the final values in particular. We remember coherence maximal values within the past. Okay, so the past is very state-like now. Now, this will be our first graph in some abstract notion of recurrent set. And we're still able to do an extension on this graph. Why? This extension we can do there is actually somehow independent of the past. Not entirely, because it observes the values of the past, but it does not really sort of reorder with the past. So there's no reordering necessary to argue that this extension is possible. We don't care about the exact shape of the past, just what values it was producing. Okay, so in that sense, it's consistent with every possible past that we've abstracted away. Great. Now we can abstract this first iteration, you see. So two events get moved into the past. And what happens now is that we get a new graph that has the same infix and the same past as the first one we had. So it looks like the G1. And what this means is that we can repeat this construction, basically. And more interestingly is there's this one single past infix combination that is repeatable infinitely. This amounts to what is classically known as a lasso. To shortly explain lassos in the state space, in the state version, a lasso is basically a run that visits some state twice inside a loop. And because it visited the exact same state twice, we can repeat basically this loop that visits a state. Here, instead of repeating a state, we repeat an infix of a graph and the corresponding past. Okay, so in particular, this is a finite representation here. We just need this thing here, and it witnesses non-termination. Okay, great. So how does it work in practice? We basically want to find exactly such lassos. And the lasso we can witness by finding a single concrete execution of the system that has this specific shape here that repeats some infix. For example, it could be this graph here. And we need to check two properties. The first one is, if we abstract all the history up to the first infix repetition, and we abstract all the history up to the second repetition, then we must get the same graph. So this graph here and this graph must be the same. Okay? This says the pass and the infix sort of repeats. But this is not sufficient yet, because it might have been the case that the infix was only repeatable because we started from a very concrete pass. It might have been the case that the second infix was only reachable due to having the very concrete past here. So what we also need to check is that after we have abstracted the first pass from up to the first infix, that from there on we can still do a repetition of the infix. So this is an abstract extension in some sense. And actually this step is where consistency checking and fairness checking is embedded, that I somehow omit in this talk, but this is sort of the interesting part in theory. But if we prove both of these things, then we actually have a lasso. And this lasso witnesses non-termination. Now, the great part is that because this lasso is somehow induced by a very concrete execution, we can use tools that look for very concrete executions. And there are many such tools. For example, GenMC, Herd, Deagle, Nithag, D'Artagnan. All of these tools are working on this execution graph representation. And we decided to adapt D'Artagnan. It's an SMT-based bounded model checker, which basically means that we add an encoding into D'Artagnan that, on one hand, decomposes, so it guesses a decomposition of an execution, just like at the top here. And then we encode these checks that you see there also in a formula. We put all of that in a formula, append it to whatever D'Artagnan already does, and now it finds such lassos. That's the basic idea. I won't go into the details. Okay, so we've evaluated this on some benchmarks. What we were interested in is, so our theory supports unfair schedulers. Again, I've not shown this in particular. Fair memory reasoning, weak memory reasoning, and also complex side effect for loops. And for this talk, I will just focus on two sets of benchmarks that expose some of these features. So the first one is a library of concurrent data structures and locks called libvsync. And this library is correct under weak memory. So it's both satisfies, so the locks in that library satisfy liveness and safety, so mutual exclusion. But you can relax barriers inside those implementations in such a way that some of these locks start to fail liveness, but they're still safe. So mutual exclusion is still guaranteed. What this means is that now you end up with benchmarks or with code that on one hand requires reasoning about weak memory because it's related to barriers. Under sequential consistency, everything would be fine. And secondly, a safety checker would not be able to find such problems because it's safe. It's only the termination that, the liveness that gets problematic. Now, the point here is that D'Artagnan is able to find all issues in the code. GenMC can also find many issues, but it sometimes needs manual annotation help to do so. And now you might be wondering, why do you have all this theory if there's already a tool that can do it? The point here is that these benchmarks have very simple loops that are spin loops. They do not produce side effects, so they're wait loops. And for those wait loops, a sort of easier theory suffices to argue about non-termination. So they're somehow simple, okay? For the second set of benchmarks, we looked at GPU code. GPU code is interesting insofar that GPUs have unfair schedulers in general. I won't go into detail how the schedulers work, but there's, apart from the fair one, there's various versions of unfair scheduler models. And we looked at litmus tests, and we found, unfortunately, got a lot of unknown results on existing litmus tests, but this was simply because these tests were terminating, and as I said, initially we only do non-termination, not termination proving. But because all of them were terminating, it means that we, in contraposition, basically, we found all termination violations. If there was one, we were able to find it. We also looked at more realistic prefix sum implementations. Prefix sum, again, I won't explain the details of this algorithm, but basically, some data is split onto or computed partially on different thread clusters. And these clusters or these threads at the end will accumulate their partial results. And the way they accumulate these results, they might have to have some assumptions on how they get scheduled to get this accumulation correct, or that they don't starve. So there are different implementations that work under different schedulers. And there's even one on the bottom right that works under any scheduler. Very interesting. So even if the scheduler is totally unfair, it works. So these results are actually in some sense known because people expected these results. But to the best of our knowledge, it's the first time that we could actually prove them automatically. What is a little bit unfortunate is that it turned out that all these, so we did these checks under the real GPU memory models, but it turns out that under SC we get the same results, so under sequential consistency. That means on these benchmarks, the memory model didn't really play too much of a role. So our GPU tests were not really exposing the weak memory aspect of our theory. Okay, and with that, I want to conclude my talk. Thank you for listening.
All right, we have a time for a few questions.
Okay, so I actually have 3 questions, so I don't know how many of them I ought to ask. But, so the first question is, so if I understand well, in your introduction, you said that for some kind of, in some situation, you need to rely on some fairness assumptions of the scheduler in order to prove non-termination.
Not on the scheduler, on the memory model,
Right.
So we don't have, yeah, but these assumptions are always satisfied.
Okay.
Yeah, yeah.
What I don't understand is, so non-termination is a safety property, right? You essentially prove that you never end up in a final state.
Okay.
Fairness is a liveness property.
Yes. No,
You
I think
shouldn't rely on a fairness property on a liveness property to prove a safety property.
No, I think non-termination it requires fairness. So you are saying that you shouldn't need fairness reasoning? Or
Well,
what
yeah.
No, this is not true because, for example, if you have, I mean, just take the example with a scheduler here. Do I find it quickly? Basically, in this example here, I extended the second thread all the time, and I said the scheduler is unfair and the first guy never gets its turn, right? If the first guy actually ever gets its turn, he will cross through the critical section, and he will then eventually say, look, I'm done. You can enter now. And then the second guy will have to enter. So this will terminate under a fair scheduler.
So you rely on unfairness.
Sorry?
So you rely on unfairness.
Inference?
Don't rely on fairness, you rely on unfairness.
Now, in this particular, I assumed an unfair scheduler, but you can, it's parametric. Our notion is parametric in a scheduler. So if we give a fair scheduler as our assumption, then our theory won't show non-termination here. So you give us both the notion of memory fairness and the notion of scheduler fairness.
Is there cases where you assume fairness and you prove non-termination?
Yes, but you say what kind of fairness assumption we do. So you can say don't do a fairness assumption. We say, okay, it doesn't terminate if there's no fairness. Or you can say assume fairness, does it terminate? And then we say maybe yeah, it still doesn't terminate or no, it terminates. So the fairness assumption is parametric. But you need some fairness assumption to understand. So the fairness implies whether termination will hold under this fairness assumption or not.
Maybe we take this one off.
Yeah, sure.
So can you unomit some discussion of the fairness? You kept saying you're going to
Unomit, okay.
So like in the lasso, you maybe need to say that the lasso has
Yes,
everyone
yes. So
being
for
live.
example, here, this extension here, the second point we have to prove here, right? What we want to ensure, let's say your scheduler is fair and says everyone has to get this chance. Then the extension from the first infix to the second infix has to make a move for every thread. If every thread makes a move, then this is fair. But if you have a totally unfair scheduler, then it's fine that only one thread makes a move to repeat the infix. So here you ensure that this is a scheduler fairness. Memory fairness also exists. Memory fairness says threads need to see newer and newer values in memory if they are newer values. They cannot forever read stale values from the cache, say. So that means they have to progress along the coherence order. So they cannot read the same write over and over again. So this will also be here in this extension relation. It ensures that everyone makes steps forward in a coherence relation when observing new memory.
Does that mean your abstraction of the past has to record like where people are in the coherence order?
Not exactly in this particular case. No, actually, it's the opposite direction. Because we know that everyone will progress due to memory fairness, we are able to abstract a lot of the past because eventually it becomes invisible. They cannot stay forever in the past. They have to progress.
Okay, so unfortunately we're out of time, but we can take the rest of the questions in the break. So let's thank the speaker one more time.
machine learning session. I'm Satnam Singh, and it's my pleasure to welcome Timothy here, who's going to give a presentation, Chop Chop, a programmable framework for semantically constraining the output of language models.
Is my microphone on? Can everyone hear me? Oh, can you turn on the microphone? Can everyone hear me now? Is it working? Yes? Okay, great. Okay, so I'll start. Okay, so I'm Timothy. I'm presenting our paper Chop Chop, which is about semantically constraining language models. And this was joint work done with all of these great people at UCSD. Okay, so what is this talk about? So this talk is about how we can enforce formal specifications in LLM-generated code. So let's say that we have some programmer, let's say Alice, and Alice is using one of these coding LLMs to help her write some code. But Alice also has some kind of formal specification in mind. This could be like a variety of things. It could be expressed in a program logic. Maybe it's a specific type signature, or it's like some static analysis that the program that the LLM returns should satisfy. But regardless of what the specification is, right, how can Alice get a guarantee that the program that the LLM returns satisfies the spec she has in mind? So in this talk, I'm going to show you our framework for constraining LLMs to return code that only satisfies specifications. And the key thing to note is that I'm using the word framework here, and that's because our method is parametric over an encoding of your specification. So that means that you can encode whatever type of specification you want in our system. And so for this paper, we used two different case studies that are specific instantiations of our framework. So I'll talk about these later, but the first one is we constrain the LLMs with some kind of equivalence constraint to a reference program using egraphs. And in the second case study, we constrain LLMs with respect to type safety for a subset of TypeScript. But you might be wondering, so what is the point of this framework in the first place, right? Why do we need a framework for this? Because there's sort of like an obvious solution that you could use to ensure that the output of the LLM satisfies a formal specification. And that's basically just to hook up the LLM and a verifier in a loop, right? So this naive approach is called rejection sampling. And basically, you just ask the LLM to generate a whole program. You put it into a verifier. If the verifier says yes, we can just return it to Alice, no problem. And if it doesn't, we can reprompt or retry with the LLM. And keep on doing this a couple of times, and hopefully eventually we get something that works, right? But there's sort of an obvious problem with this, right? Which is that this might take many iterations. And maybe the underlying issue is that we're not giving the LLM any feedback until it's generated the whole program. So first of all, this cycle might not even terminate if the LLM sort of spins its wheels forever. And it's also computationally inefficient. And so in some sense, what we're really not doing here is maximizing the value of our specification, because ideally we would like to use the specification to inform the generation process, right? In this kind of naive rejection sampling approach, the specification isn't being used until we've generated the whole program. So to sort of fix this issue, people have come up with this idea called constrained decoding. And so I'm just going to explain this idea with a simple illustration toy constraint. So let's say that we're asking a LLM to generate a Python signature. So just a bit of background on how LLMs work. If the LLM has generated some text, like maybe def, internally how LLMs work is they'll maintain a probability distribution over which tokens can come next. So maybe this is foo, AB, open parentheses, and 1. And normally, the LLM is just going to sample from this distribution sort of willy-nilly. It's going to be able to pick any of these tokens. But the idea of constrained decoding is that we're going to do some kind of analysis on each of these tokens. And so we're going to ask if we add each of these tokens to the text that we've generated so far, is this a prefix of something that satisfies our constraint, which in this case is being a valid Python function signature. And so we're basically going to maintain this invariant throughout the process that whatever text the LLM has generated is always a prefix of a valid program. And so in our example here, because Python function signatures can only start with identifiers after the def, and they can't start with numbers, we can remove these two tokens, and we'll stop the LLM from picking them. And like I said, we're going to keep on maintaining this invariant, and this process will continue for 2 or 3 more tokens until eventually, let's say that the LLM finishes something, and we get something that's correct by construction, because we've been maintaining this invariant the whole time. So, like the thing that we saw in that example is that like the core analysis that we need to do is to check if that the text the LM has generated is a prefix of some kind of valid program, right? And valid program there was like a very like basic constraint, like maybe you could enforce it with some kind of like regular expression or something. But in the examples I mentioned earlier in the talk, like with this egraphs and types thing, like these are like sort of like much harder properties, right? So the question of this talk is how do we build these kinds of prefix analyses for these more expressive properties? So let's look at sort of like what the ideal interface that we'd want is. So if we have some kind of like abstracted formal specification phi, and we had some kind of checker like P models phi, what I want is I just want to like input this checker, and then I want to magically, like through some black box process, derive a constraint decoder, which again is just doing this prefix analysis idea of checking if a prefix omega has a completion satisfying phi, right? And so this is what we would like in theory, and there's sort of some limitations of existing constraint decoding strategies that do not really realize this picture. So in particular, there's sort of like two classes of current approaches to constraint decoding. One is grammar constrained, and two is handwritten constraint decoders. So let's look at how these approaches sort of fail to meet this ideal picture. So in grammar constrained decoding, we restrict the class of constraint to specifically be about context-free grammars. So this means that we can only talk about things involving like syntax. So the good thing about this is that you can sort of just input an arbitrary context-free grammar, and it's very like configurable. You can change the grammar however you want. But the bad thing is that for those properties that we mentioned earlier in the talk, like egraphs and types, those are not like context-free languages. They're not like really syntactic properties. And so we can't really use this if Alice wants like type-safe programs or something, for example, right? And it's worth noting that this grammar-constrained decoding is used in industry a lot. So if you know the name like structured outputs, this is like really grammar-constrained decoding under the hood. And it's being like used now by big companies like OpenAI, Google, and Anthropic. So if we want to have these more expressive constraints like type safety and like egraphs and so on, another option is we could just manually implement the constraint decoder ourselves. And some existing work has done this as well. And so the idea here is that we'll fix a specific phi, and we'll just like manually like think really hard and come up with some constraint decoder implementation for phi. And so like some papers have done this, like I said. So there's this paper from PLDI last year that did it for type checking. There's this paper from NeurIPS a couple years ago that did it with some simple static analyses. But the problem here is that we had to be like very manual and very deliberate in crafting this thing. Like if we want to like program the constraint, it's not like the easiest thing to come up with, because as we'll see in a second, it's like not actually that trivial to like program these kinds of analyses like by hand, and it's like very nasty to think about. And so what we're left with is like this like really unsatisfying picture, right? So if you can kind of imagine like two axes of constraint decoding. So one axis of like desirability is programmability. Like can we change the constraint and like have some kind of like parametric interface? And the grammar constraint stuff is like great for that, because a context-free grammar is sort of like a nice declarative specification that we can use as like a parameter to build a constraint decoder for us. And the flip side is that the handwritten stuff can do like very expressive kinds of constraints, like type safety, but people have to come up with the constraint decoders themselves in like a very manual fashion. So this paper is aimed at sort of being the best of both worlds and being in this like top right corner here, and that's we're trying to be both programmable and expressive, and that's what I'm going to show you today. So how do we accomplish this, right? So the idea is that we are going to provide like almost a minimal interface and then derive the constraint decoder for you. So concretely, to use our framework, users are going to provide two inputs. So the first input is just a grammar-like thing defining the syntax of the language. So if you used a tool like Yak or something before, it's like very similar to this, and it's basically just defining the concrete syntax of the language. And then the other thing that users have to provide is a encoding of the constraint. So in the slide title, I say almost for free, because ideally, the user would just provide the definition of their specification, and we would somehow derive the constraint decoder automatically. But we have this like almost parenthetical, because what they're actually going to provide is a lifting of the constraint. And the idea is that's going to borrow from the sort of classical idea in program synthesis of like pruning. And what this is going to encode is how their constraint acts on sets of programs. So the idea is that given a set of programs, it's going to return some subset of constraint satisfying ones. And I'll talk more about like how this like concretely looks like in a little bit of a second. And so our approach really has like two core ideas, and I'm going to walk through this first idea of constraining strings through prefix spaces. And we're going to see how these inputs can be used in our approach to build a constraint decoder automatically. So let's like think about why constraint decoding is like hard to implement manually first. So let's say that S is a string, and I am in some language where, for example, it is ill-typed to add integers and strings. So let's imagine that we're writing a constraint decoder that enforces some kind of like type-safe invariant, and we're asking the question, is 1 plus s a prefix of a well-typed program? Now you might say, okay, I know the answer to this, right? We can't add ints and strings, so like the answer should be no. But as a complete program, like this is like kind of like like the picture that we have in mind. But in reality, like what if we had like a .length method on like strings, for example, right? Then there actually is a well-typed program completion in this example. And it's like very tricky, right? It's like not like intuitive that like this is the case. So like what went wrong with like sort of like the naive style of reasoning here, right? So the issue is that if you want to implement a constraint decoder, which is analyzing strings, you have to explicitly reason about things involving the concrete syntax of the language. And this includes things like what operators there are in the language, their precedence, whether the language has like left recursion, how strings lex, and so on and so forth, right? And all this stuff is like really nasty to think about manually, right? Like we don't intuitively want to have to like think about this, right? Sort of like if Alice is trying to implement her own constraint decoder, the picture she has in her head is probably something like this typing rule on the right, which is saying that numbers, like addition is well typed if like the left and the right hand side are both like numbers, right? Like this is like very like beautiful and like simple. We don't want to have to worry about like the like method syntax for a language, right? Like this would be like horrible to like program manually. And existing approaches had to kind of like bake that in and like think really hard about the specific concrete syntax of their language. So the idea of our paper is that we are going to avoid all of this, and the way that we're going to avoid it is with this abstraction called a prefix space. So the intuitive idea is extremely simple. A prefix space is just going to represent the set of all abstract syntax trees corresponding to programs starting with a prefix. So as an example, let's say that our prefix is 1 plus s. Then the prefix space for 1 plus s is going to be an infinite set, and it might contain trees like 1 plus s, 1 plus s plus 2, or 1 plus s times 2. And notice that these are all parses of programs that start with 1 plus x, if you think about them like as text. And I wanted to pay specific attention to that third example here, because we can see that like based on like how things parse, the abstract syntax trees that we represent in the space, the nodes might not like sort of be connected when you think about what's in the prefix and what's not. Like there might be some like distance between like the plus and the s, for example. And so it's like a little like strange to think about. And like this is like the core idea behind like abstracting away these like nasty details about concrete syntax. Okay, and so the idea is that first we're going to build this prefix space, and when we build this prefix space, we're going to get some like space that represents like all of these programs and like infinitely many more. And we are going to take our pruning function that I mentioned was an input to our system. And what the pruning function is going to do is it's going to take this entire space and shrink it to some subspace of programs that approximates the set of constraint satisfying ones. And then we're going to ask, is this like shrunk subspace empty? And so if it is empty, that means that there is no program in the prefix space that satisfies our constraint according to our pruning function. And so we are going to say that the prefix is invalid. If this set is not empty, that means that there must be some program in this prefix space like satisfying the constraint according to the pruning function. And so we can say that the prefix is valid. And so to summarize, this is sort of like the formulation of like when we accept a prefix or not. So we're asking an existential question. So does there exist a program in the prefix space so that the program satisfies the specification? And I want to take special attention here to the structure of this formula, because if you're familiar with some like classical synthesis ideas, for example, like SIGIS or like realizability, you might recognize that like this is like sort of the classic setup for a synthesis problem. And we're going to see that this is going to allow us to like leverage some insights from synthesis into building constrained decoders as well. Okay, and so now that I've shown you the sort of the high-level sketch of our approach, the next thing I'm going to talk about is how users actually program this like pruning function and what the interface of the system like looks like. And our second core idea for this paper is that you can program over spaces of programs using co-induction. So the idea is that basically we're going to define an algebraic data type representing spaces of programs. So in this slide here, we've defined an ADT, and it says that a space is either empty, a union of spaces, might be a constant integer, a variable string, or it's an addition of two spaces. And so you can think of this as like an ADT for the abstract syntax of the language, but sort of just souped up with these additional like empty and union constructors. And I mentioned that we're going to use co-induction. So the key idea is that we want to be able to represent infinite spaces of programs. And co-induction is going to be a programming formalism that allows us to manipulate and construct these infinite spaces of programs. So in the example on the slide here, we defined an infinite space S. And what this definition is saying is that S is a union of the space consisting of just one and all the programs that involve X plus some program in S. So S is recursively referring to itself, which is why it's an example of a coterm. And if you're a synthesis expert, you might recognize this as like being very similar to, for example, like a version space algebra. And so the idea is that this is going to give us a great abstraction for implementing our pruners. And if Alice has this like simple typing rule in mind, there's sort of like a natural formulation using our framework of how we write the pruners. So because these spaces of programs are elements of a co-inductive type, the pruners are dually going to be co-recursive functions which act on these infinite spaces. And the nice thing is that this is sort of abstracted away from the programmer. So the implementation of the pruners is like more or less like similar to how you would write like a sort of like an ordinary type checker. That's just like doing some like pattern matching on like the cases of like abstract syntax trees or whatever. And we're just going to like get like this nice programmatic interface for free. Okay, so let's talk about the evaluation for our paper. So like I said in the beginning, we do two case studies. So in the first case study, what we do is we ask the LM to refactor simple expressions into equivalent ones. And this is like for like a toy functional language. So for example, like if we have this like distance formula on the screen here, like a valid output the LM could return is like this refactored version with like let bindings. And I say equivalent here, right? So like what does equivalent mean? So equivalence has to be like formally defined somehow. And so the idea is that we are going to use this data structure called a egraph. And we don't have time to discuss like the ins and outs of like how egraphs work, but you can just imagine that it's some data structure for representing equivalence classes of programs. And the equivalences are defined with respect to some set of rewrite rules that the user provides. So maybe this is like commutativity of addition, or the fact that like multiplication distributes over addition. So the basic idea is that we're just going to define some egraph, and then our method is going to be parametric in the egraph. So the pruner is going to take an egraph as an argument, and then return a function on spaces. And the idea is that we're just going to look at the equivalence class for the source program that we started with. And to implement the pruning, we're just going to intersect it with the prefix space that we have when we're doing the constrained decoding. And if you're like an expert on egraphs, you might know that a egraph conceptually represents a regular tree language, which is why we are able to do this intersection exactly. Okay, and then the second case study, we just do like some like simple like TypeScript benchmarks. So these are like collections of like simple tasks. So like in this example, we're trying to find like the next perfect square, and the constraint that we're enforcing here is basically just type safety. So we want the LM to output like well-typed TypeScript functions. Okay, and before we talk about the results, it's important to note that we have this great guarantee from our framework, which is that with semantic constrained decoding, we will never generate an invalid program because, like by construction, we maintain the invariant that everything is a prefix of a valid program according to the constraint. But just because we don't generate invalid programs doesn't mean that we always generate valid programs, right? So in particular, our constrained decoding method can still fail if like the LM like gets stuck and keeps on like trying like bad tokens, or if it like runs out of like some like budget which we allowed it. So let's look at our results. So this is for code llama 13b, and we have more data in the paper. So if you want to like look at all of our like results, you can look in the paper for that. But you can see that across both benchmarks, we see like a general improvement with semantic constrained decoding, and this is compared to both grammar constrained and unconstrained baselines. So in the grammar constrained baseline, all we're doing is only enforcing that the LM generates something that's syntactically valid, which is a strictly weaker condition than our semantics constrained decoding. And then in the unconstrained, we're not doing any constrained decoding at all. And OK, in terms of future work, right now, there's like a little bit of issues with like scalability. So we're not running this on like the most like expensive hardware or anything, but we empirically see about like a 2 to 3 times like slowdown when we use our approach compared to running the LM unconstrained. We're interested in making these like pruners easier to program. And then like the last thing I want to mention is that in this talk, the way that we did constrained decoding is sort of parametric over a pruning strategy. And the great thing is that program synthesis has been around for 30 years. And we have like studied all these kinds of different domain-specific pruning techniques in synthesis. So in some sense, our paper can sort of be lifted with one of these techniques to like build constrained decoders for free using like any like pruning strategy from like classical synthesis. And so we're really excited about this. So like if you have some like application in mind and you work on like such a pruning technique, please come talk to us. OK, so this is the summary of the paper. That's all. Any questions?
Thank you very much, Timothy.
OK, let me, I can ask 2 questions if there is time. OK, so first I will start with like the experimental setup. So you used code llama and not like the recent models like Cohen 3, so there has been like works on like issues found out like constant decoding actually harms performance for reasoning models. So did you observe something like that?
Sorry, I couldn't hear the last part. Can you say a little louder?
So there has been some works that says like the constant decoding actually harms like the task-specific performance for reasoning models and other.
Yeah. So this is a great question. So so there's been some like empirical papers that show that constrained decoding can like basically mess with the distribution of a LM. So the good thing about that is that it's sort of an orthogonal problem to our paper. So our lab has actually like studied like different like sampling strategies that sort of resolve those sorts of issues. And like basically the issue is that the constrained decoding can like steer the LM like out of its like probability distribution when we like remove some token choices. And like the way that people alleviate this is they like come up with like more sophisticated like sampling strategies about how to like pick tokens from the probability distribution. But those are still like using some kind of like prefix analysis that tells you whether or not a token is valid. And so like the question of like making the LM like sample more in distribution is actually like sort of like orthogonal to this paper. So like the short answer to your question is that like this is like a sort of like a like known issue and there's like known solutions, but I mean it's like a orthogonal problem basically to the paper.
So the second question is more theoretical side. So one problem with constant decoding is like the tokens that are generated by LLMs is not like the exact characters that defines like the formal language, like the alphabet, right?
Right.
The token misalignment problem. So
right.
One of the main problems is sometimes like how you ensure like soundness for like different tokenizers in like more problematic case, like when multiple tokens represents a single character. So is like does your framework suppose new tokenizers or?
Yes. So the question is basically the tokens the LLM outputs might not correspond to the like lexical tokens in the language. And yeah, like this is like a known problem. And the short answer is that when we're constructing the prefix spaces, we basically have to like take this into account and like do some kind of like analysis about which ways different tokens can lex. But we do support this in our framework. And like it's not a problem for us.
Let's take one more quick question.
Yeah,
Joey can set up that simultaneously.
I just have a quick question. In some settings, does this boil down to type inhabitability?
Yes.
And given that, I'm wondering your guarantee on slide 44. Like, how do you guarantee that in that setting?
Yes. This is a great question. So so we're asking if in some space of programs if there's like a well-typed term. So yeah, you can imagine it as like a type inhabitability, like type formulation. And like you might know that like some of these like type inhabitability problems might not like be decidable if like the type system is like sufficiently expressive. So the answer that I like kind of skimmed over in the talk is that the pruning function is probably going to be approximate in some kind of sense. So like we have more details about this in the paper, but the like short answer is the user will encode some kind of approximation instead of like an exact like pruner. And then we still get like some like soundness guarantees even if like the user enforces like an approximation, but like more details can be found about that in the paper, I guess.
Let's thank Timothy for a great talk. Joey is going to talk to us about compiling to linear neurons.
All right, can you hear me fine? Is the mic on? Yeah, cool. So yeah, I'm Joey. I'm a PhD student in the PL group at the University of Pennsylvania. And this is a joint work with my advisor, Steve Zdandrovic, Conrad Cording, and also in collaboration with Neda Amin, who's at Harvard. So the question we're interested in this work is how do you take a differentiable programming language and extend it with first-class discrete structure? So this means that something as simple as like a conditional, you can use it wherever you want in the language and things don't break. So for instance, in these languages, they're very popular in machine learning for implementing things like neural networks. But when you're implementing neural networks, you can't just throw a conditional wherever you want because you can easily break the derivatives that these networks need in order for learning to work. But these are issues that compilers can ultimately correct, and this talk is essentially about how you do that. Now, to begin, I want to introduce a simple problem that'll help kind of illustrate what kinds of programs you can and can't write in these differentiable programming languages. So the problem is just about conditionally transforming an input image. Now, if the input image is a 1, don't do anything, just apply identity. But if it's something other than a 1, you should try to transform it into a 1. Now, what's nice about this task is that it has both discrete and differentiable structure. So the discrete structure is just the conditional, and the differentiable structure is transforming that image into a 1. So that's not something you just sit down and try to write. That's typically something that you try to throw a bunch of data at a neural network to learn. So a typical approach in differentiable programming languages is what we're going to call the indirect approach. And we call it an indirect approach because you're not trying to directly specify the conditional structure of the task. Instead, what you're going to do is you're going to try to set up like the skeleton or an architecture to solve the problem. And this kind of pseudocode that I have here is just kind of prototypical of the kinds of code that you would write in a differentiable programming language. And again, what you're trying to do is just set up like the skeleton of a network. And the important kind of mental model that should be in your head, especially if you haven't used a differentiable programming language before, is that you're just defining some kind of function over a vector. And what you're ultimately going to try to do is instead defer to learning to figure out what exactly these W's should look like, which are matrices. Now, this is essentially the main approach that people use in machine learning, which has been overwhelmingly successful for all kinds of things, right? Like language modeling, image recognition. And this is the main way that you program in languages like PyTorch and JAX. But one key issue with this style of programming is that it crucially depends on getting the architecture, the skeleton of the network correctly. So you can easily set up an architecture or a skeleton that doesn't help you learn some task. And so in practice, you actually have to experiment a lot to get things to work, especially if you're in a domain that hasn't been studied extensively. So we're interested in how to constrain that search so that maybe you can use a compiler to help find what the right architecture could look like. I should also say that sometimes this process of like experimenting to find an architecture is called in like a tongue-in-cheek way graduate student descent, because you basically just throw 1,000 grad students at a problem, and then you slowly start to figure out like, oh, this kind of circuit motif is useful for the task. So our work is trying to explore a more direct style of programming where in the cases that you have discrete structure in the task, you can actually just try to specify it. So in this approach, you could write a program that looks something like this, where you're writing a program that decomposes the task into first detecting if the image is a 1, and then if it's a 1, you apply identity, and otherwise apply a transformation to turn the image into a 1. And so hiding in this program is still some element of the indirect approach. You have to specify the network or the architecture for learning what a 1 is, or for transforming an image into a 1. But you're decoupling now the conditional structure of the task into simpler parts. So it's way easier to design a network to detect if an input image is a 1 than it is to do the entire task altogether. But for this to work, you need to somehow be able to compile that program above into the network below. And in order to explore the design of these compilers, we introduced a minimal calculus that we just call Cajal. So Cajal is a small language. It's basically just Booleans and higher order functions. But for now, it's more than enough to basically deal with the conditional image transformation problem. At the end of the talk, I'll mention how you can go far beyond just these simple data types. So I just want to briefly talk about what a linear neuron is. And they're effectively just linear maps. So the exact definition of what a linear map is not super important for this talk. But it looks something like this. And the important thing to note, though, is that a linear map could be represented as a matrix, and that this matrix is actually specifying the coefficients of some linear neural network. Now, there's a world where we could have just called the paper compiling to linear maps, but we chose to emphasize the linear neurons perspective because they're a much more specific kind of mathematical object. So there are tons of linear maps that you can't implement in JAX or PyTorch, or that look anything like a neural network. So drawing on some very nice insights from the semantics of linear logic, we decided to give a linear type system to Cajal. And it turns out that if you give a system linear types, you're giving it some chance to be, for the programs to compile to linear maps. There's a long understood connection between linear types and linear algebra that we're exploiting in this work. So with nonlinear typing, the issue is that you can freely duplicate assumptions in your typing judgments. And in short, what this will mean behind the scenes is that when you're trying to define a semantics for your language and compile them to linear maps, often the fact that, for example, in this program, you're duplicating the assumption that x is a Boolean causes issues in your proofs. And so these structural properties of the type system have a deep, deep implication on your ability to do this kind of a trick. So with linear typing, again, you're not able to do this. It's a lot more restrictive on how you can duplicate assumptions in a context, for example. And so behind the scenes in Cajal, linear typing is doing a lot to make sure that we can take a program like the one above and compile it into something like below. And so now I want to talk a bit about how exactly the compiling would work for a conditional, but I want to start with an example that doesn't work, but it's almost there. So what we're doing here is compiling a not operator. If you instantiate x with true and evaluate it, it should give you false. Instantiate it with false, evaluate it, should give you true. And the way that the rules work, or the ways to understand the rule, is just the compiler, which I'm denoting with denotation brackets, is taking a typing judgment and returning a function of some vector, sigma. Exactly how the variable rule works is not deeply important, but what you should understand is that the compiler is taking a judgment and spitting out some function between vectors. For constants like false and true, it returns a constant function. In the case of false, it always returns vector 0, 1. In the case of true, always 1, 0. In the paper, we talk a lot about what goes wrong if you try to make different choices at this stage. But again, for the conditional example, it's not super important to understand. Now, for compiling conditionals in this way, which we call like a kind of hard branching conditional, what you're doing is you're just checking if the first component of the vector of the compiled condition is 1. So I should also say that this rule is kind of emblematic of what would happen if you tried to naively implement a conditional in something like JAX or PyTorch, and exactly why you don't see conditionals so often in the middle of like a training loop in a neural network. So this rule has actually some very nice properties. If you, for example, passed in the denotation of true, you would get back the denotation of false. If you pass in the denotation of false, you get back the denotation of true. So it's mirroring the behavior of the source program in some nice way. But the problem is that despite the function even being differentiable almost everywhere in sigma, the derivative is just completely uninformative. So the derivative is measuring how a change in, for example, alpha 1 and alpha 2, or in sigma, corresponds to some change in the actual output of the rule. And the actual output of the rule is only ever going to be 1, 0 or 0, 1. It doesn't depend in any non-trivial way on alpha 1 or alpha 2. And what that means as a consequence in a neural network is that if you put this in the middle of the network, the way that the learning algorithm works, it would basically block the flow of derivatives to any part of the network that precedes it. So it would essentially break your ability to learn. The remedy we take in our work is to consider something like soft branching. So with soft branching, what's effectively happening is that you're sort of compiling each branch of the conditional, running both, and then combining them and scaling them according to the compiled condition. So we compile assumptions in the exact same way. And like before, if the input is sigma, or the input to sigma is the denotation of true, you get false, vice versa. So it also mirrors the behavior of the source program in a nice way. But unlike before, you can actually get informative derivatives from this kind of an equation. So for example, you can get non-zero derivatives. And if you place something like this in the middle of the network, you wouldn't block gradients in the same way that the previous rule would. So we use a rule like this to compile a program like that above into a network that looks like that below in Cahal. So I won't go through the rest of the compiling rules here, since it's not necessary for the motivating example. But in the paper, we talk a lot about the interesting things that pop up when you try to compile lambdas and applications. And those formal specifications are ultimately checked by a correctness theorem. So it might be helpful to just think of the correctness theorem as equivalent to the soundness and adequacy of a denotational semantics. But more intuitively, what we're asking of the correctness theorem is just, can we predict what the compiled code is going to do? So in this case, can we predict, if we know how a program evaluates and what it doesn't evaluate to, can we predict what the compiled code is also going to evaluate to, or what it's equal to, or what it's not equal to? And if we can do those things, we call the compiler correct. Now, the appendix contains detailed proofs of all these things. But I do want to highlight one lemma that is I got wrong quite a few times in trying to state correctly, and that's doing a lot of heavy lifting in the paper. So this lemma on the bottom right basically just says that the compiler is taking programs, typing judgments, and mapping them to linear maps. And it does a lot of heavy lifting in the proofs, but also it's the lemma that kind of justifies this story I've been alluding to informally about the connection between Cahal, linear types, and linear algebra. It's also the lemma that essentially justifies the title of the paper. So in one sense, our compiler is correct, but a stronger test of correctness would be if it actually helps us solve this conditional image transformation problem, which interestingly goes beyond the notion of correctness I just told you. So to test this, what we did is we implemented Cahal. It's just a simple 200-line prototype implementation that extends PyTorch with conditionals, where in the back end, it's basically translating those conditionals into the soft branching equation that I showed you. And so we trained basically both of these networks to solve the task. And we were interested in the final outcome of learning, so did it help? But also just qualitatively, how do networks learn in super weird different ways when you use these compiled networks? So the next couple slides are just going to be zooming in on 2 examples comparing both models on how they, across training time, how they learn the task. But afterwards, I'll talk about a more generic measure of their performance across the entire test set. I'll begin with the direct approach. So remember, the task is to apply identity if the image is a 1, and otherwise to try to transform that image into a 1. And from left to right, I'm showing them intermediate model outputs across training time. So each training step just means I updated the parameters of the network, which means I've just slightly changed the function that it's computing. So in about the first 100 steps, what the direct approach is learning is to do identity for everything. So when the input is a 1, that's good, that's correctly solving the task. But when the input image is a 4, that's definitely very wrong. And in the next 100 steps, what the network learns to do is just try to stop overusing the identity for everything, especially for when the input image is a 4. And for the remainder of training, the network is just kind of refining the answer, which mostly just means it's trying to get a better and better reconstruction of the identity for when the input image is a 1. And the last images I have on the right are essentially the solutions that the network converges to after 3,000 training steps. And in summary, it sort of ends up doing the right thing. It learns the identity reconstruction on the 1, and it transforms the 4 into something that looks like a 1. Now, for the indirect approach, the learning dynamics are a bit simpler. In the first stage, it's basically just learning a constant 1 function to apply to everything. And there's a bit of noise in it. So then in stage 2, it tries to figure out how to sort of refine that answer by just removing small amounts of pixel noise in the image. And generally, what it learns to do is just apply a constant function to everything. The key distinction, though, in these models' behavior is just that the indirect approach is struggling to recover the identity for when the input image is a 1, which to me I found very interesting because this is like a stupidly simple task. So I thought, OK, this could learn it, right? But at the same time, your takeaway shouldn't be like the indirect approach could never solve this task. Right? It just might mean that you need to throw graduate student descent at the problem like a little longer to find the right architecture for solving it. But again, the point is to see if when there is discrete structure, can we not just specify it directly to avoid that kind of a search? So beyond those 2 training examples, we computed what was called PSNR, peak signal to noise ratio, on each of the models' behavior across training time. PSNR, in short, is just measuring how good of an identity reconstruction is the network computing across training time, because that was the measure that most distinguished true model performance. In short, if PSNR is high, that's good. If it's around 20, it means that the network just learned to produce a constant 1. The data in blue are from the direct model, and the data in red are from the indirect approach. And the TLDR here is just that these data are consistent with what we just observed in the previous slide. So it's not that we sort of got lucky on a specific configuration of training, but we've trained everything across 5 different seeds, different learning rates, different batch sizes. And beyond some degenerate cases where no model learns anything in the bottom row, the trends from the previous slide still hold. So the paper contains 4 additional experiments on different kinds of programs that you can write in COHAL. And again, the data are, in short, consistent with the story I showed in the conditional image transformation task. And these experiments were encouraging. So since POPL, we've gone quite a bit beyond just Booleans and started considering more interesting data. So for example, if you change the target to instead think about linear recurrent neural networks, so these are neural networks that have feedback connections, you can introduce data like natural numbers. And so what this allows you to do is introduce first-class kind of primitive recursion over the natural numbers in a differentiable programming language. Going even beyond that, you can introduce more intricate kinds of recurrence in neural networks to even account for algebraic data like trees and a list data type and stuff like that. And I'm happy to talk more in the question period about additional extensions that I think are well posed, but that I just haven't had the chance to get as far to in my notes. So I want to end on a kind of more speculative note just about the current state of differentiable programming. And this is a quote from Alan Perlis in a speech he gave in 1981, essentially about how much it sucked to program in machine code in the 50s. And basically what he's saying is just that you couldn't just take an algorithm in your head and put it in a machine. It required a ton of experimentation to get right, if you could get it right at all. And in those frustrations, he just started to think about maybe developing a high-level programming language and working on compilers. And the 50s were a very long time ago for me, so I don't know exactly what he means by programming experimentation. But absolutely, in some sense, when you program in a differentiable programming language, there is this degree of very annoying programming experimentation you have to deal with. So I think maybe we should be thinking about how to build higher-level languages for Jackson PyTorch, and maybe that means that they'll include first-class discrete structure of the kind that I'm trying to study in COHAL. With that, I thank you all for your time, and I'm happy to take questions.
Right, thank you for the talk. I was hoping that you could explain to me something about linearity in a few slides back, to the example where you define the direct approach, basically.
Sorry, which example?
The one where you say if one of image, then something image.
Oh, yeah, at the beginning. Something like that.
Right, this one's fine. Right,
Yeah.
so what I was wondering is where does linearity come in here? Because image is being used
yes,
in the scrutiny and then in the branches as well. So that was my question.
Yeah, so this is a great question. So we made an important, this was not our first choice in modeling decision, but what we're doing with Cajal is we're only modeling a linear subfragment of some bigger language. This wasn't the first thing we did, actually. And originally, we had some like more complicated linear, nonlinear calculus where you could like literally type a program like that. That turned out to be a mistake because I did a ton of proof work and found that at the end of the day, when it came to actually implementing the extension to PyTorch, the only part that was interesting was the linear subfragment. So that's not to say that there are no interesting questions in studying the extended language, but at least with respect to this task on solving the conditional image transform, all the interesting stuff is happening in the linear subfragment. And that was like a hard-earned insight. Like I literally threw away like many months of my life in prepping the actual work because I realized it just wasn't that insightful for the question.
So how come? Sorry. So how come can you have image show up both in the branches and in the scrutiny of the if?
So the way that this is modeled, like literally in Cajal, is as an open, it's an open judgment. So it's a free variable. So you can imagine replace one of image with the free variable that is just like whatever type you want, essentially. And then behind the scenes, this needs to be coerced into some vector space. Like it could be like R10 or something. But
got a question around here.
Hi. Okay, so the notion of a derivative also seems to correspond really well to like the sensitivity of a function. And sensitivity type systems also are linear type systems. And I'm wondering if you had considered using a sensitivity type system here in this setting.
yeah, I know. I'm like I'm aware of like fuzz and I haven't thought as much about where you get the most traction, where you could get traction out of using something like fuzz's type system. It's an interesting point. Mostly the reason why I haven't thought about it is I feel like there's like 3 other type extensions that are like immediately tractable and offer cool stuff to do. But I would be happy to talk more and like brainstorm about.
I should have prefaced also with delightful talk. Thank you.
I wanted to ask more about the evaluation or your approach for evaluation.
The experiments?
Yeah. Does it make sense, since you're trying to impose or make neural networks compliant with some specifications, does it make sense to use neural networks verifiers as part of your way to measure the success?
For example, like what kind of notion of success are you interested maybe in?
Like, could you ask for every image that is classified as 1, the output would be the identity, for example?
Yeah, so this kind of gets at that gap, at the gap between the theorem I proved, and then there's this experiment I need to do to show that it's like ultimately correct, right? And you're saying there's maybe some interesting way to add some machine learning to complement this. I think that sounds fine, like well posed to me. Yeah.
Okay, thank you.
The next speaker could set up as well, please. Last question.
I have a question about your example.
Yeah.
So the 2-1, can that be a constant function? What's actually being learned? What does it mean to convert something to a 1?
Sorry, say that first part.
You either return the image, or you convert it to a 1. What does it mean to convert something to a 1? Can that be a constant function?
Yeah,
What does it have to be?
Originally, when I was thinking up of the task, I thought that the network would learn like this cool, slightly different 1 for every image. But ultimately, it ends up just learning a constant 1. So if you look at like the actual behavior beyond just those 2 examples, what will happen is that for 1s, it'll do identity for everything that's a 1. And then for like a 4, a 3, a 2, whatever, it'll learn a constant 1. But I think that's more of a symptom of like the training data than anything deeply relevant to the core stuff in the talk. But yeah.
Okay. Well, thank you very much.
So the slides aren't showing up for what it's worth.
Yeah. There we go. Our next talk is by Yifan, Fuzzing Guided by Bayesian Program Analysis.
Okay, thank you. Hello, everyone. I'm Yifan Zhang from Peking University. Today, I'm going to talk about our recent work on fuzzing guided by Bayesian program analysis. This is joint work with my advisor, Zhang. Our work is based on large-scale target-guided gray box fuzzing, or LTGF for short. Given a program under test and a large set of targets, usually coming from static analysis alarms, LTGF aims to trigger as many potential new bugs as these targets as possible. LTGF operates in two alternating stages, exploration and exploitation. In the exploration stage, LTGF performs coverage-guided mutation to accumulate more seeds, which enhances its capability to detect bugs during the exploitation stage. In the exploitation stage, LTGF first conducts target prioritization. For those high-priority targets, LTGF carries out directed mutation to trigger the potential bugs associated with them. However, existing approaches for target prioritization lack a systematical design. For instance, they prioritize targets one by one in sequence. This strategy is not only ad hoc, but also cross-grained, causing LTGF waste a significant amount of time on targets that are unlikely to contain bugs. Let me use a simple example to show the limitation of existing LTGF. In this program, we run timed analysis to find potential out-of-bounds bugs. The variable A comes from the input, and depending on its value, the running goes into one of three branches. The variable A is also input controlled, so it's tainted, and any variable derived from A is tainted as well, including B and C. Since A, B, C are all used as error indices, the analysis raises three alarms, A1, A2, and A3. We also assume there are other alarms from the analysis, such as A4, A5, and A6. Now, suppose we start with just one seed, E equals 0, A equals 0. Existing LTGF first runs at an exploration stage, where the goal is to maximize coverage. Let's assume this stage successfully covers all three branches for A equals 0, 1, 2. For each coverage pattern, the fuzzer only keeps one seed. So at this point, our seed set is E equals 0, A equals 0, E equals 1, A equals 1, and E equals 2, A equals 0. Next, LTGF runs exploitation fuzzing for each target one by one. For A1, LTGF picks the seed that is closest to that target, say A equals 0, A equals 0, and mutates it for a given time. Assume 1,000 mutations in this time budget. The bug behind A1 is triggered whenever A mode 100 equals 0. So it's quite likely that one of those 1,000 mutations will hit such a value and expose the bug. Then LTGF moves on to A2. This bug only occurs when A is exactly 100. With 1,000 random mutations, the chance of hitting exactly 100 is extremely low. So it's very unlikely we will trigger this bug. For A3, the situation is even worse. Here C is always odd, so C mode 2 is always 1. This means the corresponding alarm is actually a false positive. No matter how we mutate the seed, we can never trigger a real bug there. So the time spent fuzzing for A2 and A3 is basically wasted. The fuzzer has almost no chance of finding a bug, yet A2 and A3 receive the same time budget as A1. This example shows why we need a more systematic way to allocate fuzzing time, so that we invest more in valuable targets like A1, instead of treating all targets as equally promising. We make the following contributions to address this problem. First, we systematically formulate it as the reachable fuzzing targets problem. To solve this problem, we then redefine the semantics of Bayesian program analysis to enable accurate prediction of target reachability and effective generalization from fuzzer feedback. Building on this foundation, we propose Bayesian, a framework that leverages Bayesian program analysis to provide semantics-aware, fine-grained, and adaptive fuzzing guidance. Finally, we demonstrate the effectiveness of Bayesian on real-world programs, showing superior bug detection performance compared with baseline approaches. Next, we first introduce the reachable fuzzing target problem, then present how our redefined semantics Bayesian program analysis enables semantics-aware, fine-grained, and adaptive guidance for LTGF, and finally describe our experimental evaluation. We first defined the reachable fuzzing target problem. The entire LTGF process can be formalized as the following loop. First, acceleration fuzzing is performed to continuously expand coverage and obtain the current seed set S. Then, several rounds of exploitation fuzzing are conducted based on S. In each round, target prioritization is used to select a target T, and exploitation fuzzing is performed with the goal of triggering bugs at target T. After several rounds, the process returns to exploration fuzzing. We define a target T as reachable if and only if, in a single round of exploitation fuzzing within a given time budget based on the current seed set S, there is a probability of at least A of generating an input that triggers T. In practice, we set A to 99%. Therefore, our problem becomes predicting for each target T the probability that T is reachable. Taking the above example, suppose our current seed set is E equals 0, A equals 0, E equals 1, A equals 0, and E equals 2, A equals 0. For the three targets A1, A2, and A3, A1 is a reachable target because within given time budget, that is 1,000 mutations, the probability of triggering the bug is at least 99%. A2 is not a reachable target because the probability of triggering the bug within 1,000 mutations is below 1%. A3 is also not a reachable target because the bug can never be triggered, regardless of how we mutate the seeds. Thus, we successfully reduce the problem to predicting for each target whether it is reachable. By prioritizing those targets that are reachable, we can effectively address the limitations of existing LTGF and improve its efficiency. We propose a framework called Bezier, which uses Bayesian program analysis with redefined semantics to predict the reachable fuzzing targets problem, thereby guiding LTGF. Its workflow is as follows. Building on the LTGF workflow, we use the redefined Bayesian network semantics to compute for each target the probability that it is reachable by exploitation fuzzing given the current seed set S. We then perform exploitation fuzzing on the target with the highest predicted reachability probability. The result of this exploitation fuzzing is fed back into Bayesian network. If the target bug is successfully triggered, we provide positive feedback. Otherwise, we provide negative feedback. Finally, as each round of exploration fuzzing completes and the seed set expands, some targets that were previously unreachable may become reachable. Therefore, we clear all accumulated negative feedback after each exploration stage to ensure more accurate probability estimation. We first illustrate the original semantics Bayesian program analysis with an example. In the code fragment, variable A is read from external input, variable B is derived from A, and variables C and D are derived from B. Finally, C and D are used as error indices. We apply taint analysis to detect potential out-of-bounds bugs in these statements. We use taint V to denote that variable V is tainted by external input, and alarm A to denote that alarm A holds. Initially, we have taint A. According to taint propagation rules, we can derive taint B and further taint C together with alarm A1 when C is used as an error index. Similarly, we obtain taint D and alarm A2. We call this directed graph as a derivation graph. Each derived tuple represents a program property produced by the static analysis. We then transform this derivation graph into a Bayesian network. Each derived tuple is modeled as a Bernoulli variable, indicating whether there exists some input under which the corresponding program property holds. Conditional probabilities between variables are defined according to the graph structure. For brevity, we set such probability to 0.8. Using this Bayesian network, we can compute the probability distribution of each variable given posterior information. For example, we obtain that both A1 and A2 have a reachability probability of 0.512. Suppose there are other alarm statements in other parts of the program, but with lower probabilities. If the user inspects A1 and then confirms that it is a real bug, we can treat this positive feedback as posterior evidence and recompute the probabilities. Since alarm A2 is connected to alarm A1 in the Bayesian network, the probability of A2 increases. However, the semantics of existing Bayesian program analysis is defined over all possible program inputs, whereas the inputs that a father can actually generate form only a subset of this. Therefore, we need to redefine the semantics to adapt Bayesian program analysis to the father setting. We redefine the semantics of each Bernoulli variable to express whether or not it is reachable by exploitation fuzzing under this new semantics. But the Bayesian network computes for each alarm the probability that it is reachable, which can be directly used to predict the reachable fuzzing targets problem. Furthermore, the outcome of each exploitation fuzzing attempt precisely indicates whether a given target is reachable under the current setting. So we can treat this further feedback as posterior evidence and recompute more accurate probability estimates. Next, we show how Bayesian program analysis with the redefined semantics can provide semantics-aware and fine-grained guidance for LTGF. In this example, the key insight is that A1 and A2 share the same root cause and are both reachable by exploitation fuzzing. That is, there is at least a 99% probability of generating inputs that trigger them. We use the positive feedback obtained from exploitation fuzzing on A1 to increase the reachability probability of A2, thereby achieving precise prioritization of alarms that share the same root causes. We will show how our approach works. The father will first select A1, which has the highest ranking, as the next target. According to the triggering condition, the probability is around 100th. So the father can quickly trigger this bug through rapid mutations and provide positive feedback to the Bayesian network. Based on this posterior information, a new probability distribution is recalculated. Since alarm A2 is connected to A1 in the network, its probability increases, making A2 the next target. The triggering probability for A2 is approximately 1/200th. So the father can also quickly trigger A2 through multiple mutations. We present a second example. For easier understanding, we make a small modification to the first one. Now variable B must be an odd number, so C and D are also always odd. As a result, A1 and A2 can never be triggered, since both C mode 4 and D mode 8 will always be greater than 0. The tent analysis produces a derivation graph with the same structure as in the previous example. However, because it does not consider precise value ranges, it over-approximates and incorrectly reports the false alarms A1 and A2. The key insight is that A1 and A2 are derived from the same over-approximation and are both unreachable by exploitation fuzzing. That is, there is a 0 probability of generating inputs that trigger them. We use the negative feedback obtained from exploitation fuzzing on A1 to decrease the reachability probability of A2, thereby accurately lowering the prioritization of alarms arising from the same over-approximation. We will now show how our approach works. The father will target A1 first because it has the highest probability. After some time mutating inputs, the father realizes the bug cannot be triggered and provides a negative feedback. Since alarm A2 is connected to alarm A1 in the network, the probability of A2 also decreases. This allows the father to skip this false alarm and focus on other potentially triggerable targets, effectively avoiding wasted time. Next, we look at a third example. Building on the previous two, this one introduces a new variable E. The value of E is set to 1 only when the external input is a multiple of 1,000. Otherwise, it is 0. If E is 0, then C and D become 0 only when B hits an exact magic value, such as 100 or 200. In that case, they may trigger the bugs at A1 and A2. But if E is 1, we don't need an exact magic value anymore. It's enough for B to be a multiple of 100 or 200 to trigger A1 or A2. The derivation graph from tent analysis, again, has the same structure as in the previous examples. Here, we show how our approach uses adaptive guidance to help the father make better decisions at the different stages. At the beginning, The father has no seeds with e equals 1. At this point, the probability of triggering the bugs at A1 and A2 by random mutation is extremely low because it would require mutating B to an exact magic value. The key insight is that A1 and A2 are both constrained by the same input condition, and under the current seed set, they are both essentially unreachable by exploitation fuzzing. And that is, the probability of generating inputs that trigger them is below 1%. We use the negative feedback from exploitation fuzzing on A1 to deprioritize such targets that are unreachable under the current seeds. We will now show how our approach works. The father will first target A1. After attempting mutations for well and failing to trigger the bug, it gives negative feedback to the Bayesian network. Since alarm A2 is connected to alarm A1 in the network, the probability for A2 also decreases. Thus, the father can skip the currently unreachable alarm A2 and focus on other potentially reachable targets, avoiding wasted time. After another round of exploration fuzzing, the father has accumulated more seeds and now has seeds with e equals 1. At this point, we clear all previous negative feedback. The insight is that with the new seed, the input constraint statement is overcome, and both A1 and A2 become reachable by exploitation fuzzing. That is, there is at least a 99% probability of generating inputs that trigger them. By applying negative feedback elimination and use the updated result of exploitation fuzzing on A1, we prioritize targets that become reachable again. We will show how our approach works. The alarm with the highest probability is still A1. The father will again target A1. According to the new triggering condition, the probability is about 1/100th. So the bug can be triggered through mutation in a short time. The father then gives positive feedback to the Bayesian network. Since alarm A2 is connected to alarm A1 in the network, its probability increases, making A2 the next target. The triggering probability for A2 is approximately 1/200th, so it can also be triggered in a short amount of time. We conducted experiments to evaluate the effectiveness of our approach. We built Bayesian on top of the LTGF2 fish fuzz and used a taint analysis based on SVF. We compare our approach with the following baselines. The first one is prospector, the SOTA in LTGF. The second one is fish fuzz, the foundational fuzzer of our approach. The third one is fun fuzz, the SOTA of coverage-guided gray box fuzzing based on non-Bayesian Lattice static analysis. We include the fun fuzz to demonstrate that Bayesian program analysis provides stronger guidance for fuzzing than conventional static analysis. The last one is the AFL++, the foundational fuzzer for all three baselines as well as our approach. We use the same benchmarks as prospector, including 24 real-world programs with various input formats. We also use the same metrics as prospector. We measure the median time to exposure, or TTE for short, across 10 repeated runs. TTE represents the time required to trigger a bug for the first time. Our time limit is 60 hours, and the total experimental time amounts to approximately 9.86 CPU years. We use a Venn diagram to illustrate the bugs discovered by different fuzzers. Compared to other baselines, Bayesian is able to find 3.25 to 13 times more unique bugs, which clearly demonstrates its significantly stronger bug-finding capability. We further use bug discovery curves over time to provide a more direct visualization. As shown, Bayesian does not have a leading advantage in the first 40 hours. However, as a large amount of feedback accumulates, its strong guidance ability becomes apparent in the final 20 hours, clearly surpassing the other baselines. This further demonstrates the effectiveness of Bayesian program analysis in guiding fuzzing. We measure the computational overhead of Bayesian inference. On average, the time spent on Bayesian inference accounts for approximately 0.31% of the total running time. Therefore, the overhead introduced by Bayesian program analysis is tiny and fully acceptable in practice. We conducted application experiments to verify the necessity of removing negative feedback. As time progresses, many bugs become reachable, and if negative feedback is given prematurely, we may lose the opportunity to trigger them. In fact, the configuration without removing negative feedback discovers 16 fewer bugs in the end. Therefore, removing negative feedback can significantly enhance bug finding capability and is highly necessary. Finally, we use Bezier to test the latest version of software, including the most recent commits for the 24 programs used in our controlled experiments, as well as popular projects with a high number of stars in OSS files. Both groups of software have been extensively fuzz 24/7, yet we are still able to discover a large number of important new bugs. In total, we found 39 bugs, 30 of which were assigned CVEs. We present some of the bugs we discovered. On the left, we show the 4 most influential bugs, with GitHub repositories have between 7.6 thousand to 26.7 thousand stars. On the right, we show several other high-impact bugs. Overall, our approach demonstrates strong practical value in real-world software engineering. Finally, I will give the conclusion of our work. First, we systematically define the reachable fuzzing targets problem and redefine the Bayesian program analysis semantics to enable accurate prediction of this problem and further feedback generalization. Next, we propose Bezier, a framework that leverages Bayesian program analysis to provide semantic-aware, fine-grained, and adaptive fuzzing guidance. Then, we extend Bayesian program analysis beyond static alarm ranking to automated fuzzing guidance for bug discovery. Last, we demonstrate the effectiveness of Bezier on real-world programs, showing superior bug detection performance compared to baselines. And that's all. Thanks for listening.
So thank you for the talk. I wanted to know, so how do you determine that it's a bug? Here you were using out-of-bound array indexes, but do you typically do fuzzing? Sorry, I'm a bit unfamiliar with fuzzing. Do you typically do this by comparing against a set of tests and you fuzz the inputs? But how does that typically work?
Sorry, can you speak?
Yes, sorry. So I'm wondering what kind of bugs can you detect using fuzzing?
What kinds of what?
What kind of bugs? Like just out-of-bound indexes, or?
There are address errors. We use ASAN, address sanitizers, such as heap buffer overflow, out-of-bounds write read, and null pointer dereference. All about memory errors. Yes.
Thanks.
Okay.
If there's no more questions, maybe we can finish a bit early there and go and see some posters. Thank you very much.
Okay, thank you.